Hello and welcome to this course on machine learning with Python, where you will learn about applied machine learning using Python tools. Python dominates the machine learning landscape today. According to recent surveys, it is the most widely used language for machine learning, data science, and analytics. Libraries, such as Scikit-learn, are especially popular with practitioners in this field. Whether you're starting your career or enhancing your skills, this intermediate-level course will provide you with a solid foundation in applied machine learning, paving the way for advanced career opportunities in the field of machine learning, data science, and AI. To gain maximum learning from this course, a working knowledge of Python, Pandas, NumPy, and data preparation and data analysis with Python is recommended. Familiarity with the field of machine learning will be an added advantage. In this course, you will become aware of the role of machine learning in various career paths. You will gain a foundational knowledge of the machine learning lifecycle and how machine learning models work. Throughout the course, you will focus on machine learning modeling techniques such as classification, regression, and clustering. Using real-world data, you will learn how these models fit within the broader supervised and unsupervised learning frameworks. You'll also get a brief introduction to advanced methods such as reinforcement learning, deep learning, and the world of artificial intelligence. You will gain hands-on experience with building, assessing, and validating various classification, regression, and clustering machine learning models using Python and popular open-source libraries such as Pandas, NumPy, and Scikit-learn. You will gain a comprehensive understanding of machine learning using Python through instructional videos and then practice the concepts learned in hands-on labs. You will assess your learning with practice and graded quizzes and strengthen the mastery of concepts with reference materials such as a glossary. A concluding final project in the last module will provide you with the opportunity to apply your knowledge. Each lesson has one or more labs that reinforce the instructional videos by applying what you've learned in each lesson. Lab topics include multiple linear regression and logistic regression, prediction, fraud detection, KNN, and SVM. We're glad to have you with us as you start your journey in machine learning with Python. If you have any queries regarding the course material, please don't hesitate to contact us in the discussion forum. All the best. Welcome to Machine Learning Techniques and Applications. After watching this video, you will be able to explain machine learning, identify machine learning techniques, and describe applications of machine learning. Artificial intelligence, or AI, makes computers appear intelligent by simulating the cognitive abilities of humans. AI is a general field with a broad scope. It comprises computer vision, natural language processing, generative AI, machine learning, and deep learning. Machine learning, or ML, is the subset of AI that uses algorithms and requires feature engineering by practitioners. Deep learning distinguishes itself from traditional machine learning by using many layered neural networks that automatically extract features from highly complex, unstructured big data. Machine learning teaches computers to learn from data, identify patterns, and make decisions without receiving any explicit instructions from a human being. ML algorithms use computational methods to learn information directly from data without depending on any fixed algorithm. Machine learning models differ in how they learn. For example, supervised learning models train on labeled data to learn how to make inferences on new data, enabling them to predict otherwise unknown labels. Unsupervised learning works without labels by finding patterns in data. Semi-supervised learning trains on a relatively small subset of data that is already labeled, and iteratively retrains itself by adding new labels that it generates with reasonably high confidence. Reinforcement learning simulates an artificially intelligent agent interacting with its environment and learns how to make decisions based on feedback from its environment. Selecting a machine learning technique depends on several factors, such as the problem you're trying to solve, the type of data you have, the available resources, and the desired outcome. A classification technique is used to predict the class or category of a case, such as whether a cell is benign or malignant or whether a customer will churn. The regression/estimation technique is used to predict continuous values, such as the price of a house based on its characteristics or the CO2 emissions from a car's engine. Clustering groups of similar cases, for example, can find similar patients, or can be used for customer segmentation in the banking field. The association technique is used to find items or events that often co-occur, such as grocery items usually bought together by a particular customer or market segment. Anomaly detection is used to discover abnormal and unusual cases. For example, it's used for credit card fraud detection. Sequence mining is used to predict the next event. For instance, the clickstream analytics in websites. Dimension reduction is used to reduce data size, particularly the number of features needed. And finally, recommendation systems. This associates people's preferences with others who have similar tastes and recommends new items to them, such as books or movies. We'll cover some of these techniques in the next videos. To train your machine learning model on supervised data, you can select between the classification or regression technique. Classification categorizes input data into one of several predefined categories or classes, and then makes predictions about the class membership of new observations. Regression is different from classification. It does not make predictions about the class membership of new input data. Regression predicts continuous numerical values from input data. Clustering is one of many unsupervised machine learning techniques for data modeling. It's used to group data points or objects that are somehow similar. For example, in this chart, we use a clustering algorithm to represent data points in green, red, and blue color. The uncategorized data points represented in black color are considered noise. Let's look at some applications of machine learning now. This is a human cell sample extracted from a patient. It has some unique characteristics. For example, its clump thickness is 6, its uniformity of cell size is 1, its marginal adhesion is 1, and so on. An interesting question we can ask by looking at this chart is this a benign or malignant cell? Compared to a benign cell, a malignant cell invades its surrounding tissue and spreads around the body. Identifying the cell type early can be the key to the patient's survival. One could easily presume that only a doctor with years of experience could identify the cell and confirm if the patient is developing a cancer or not. Imagine you've obtained a data set containing characteristics of thousands of human cell samples extracted from patients believed to be at risk of developing cancer. Analysis of the original data showed that many of the characteristics differed significantly between benign and malignant samples. You can use the values of these cell characteristics in samples from other patients to indicate whether a new sample might be benign or malignant. You should clean your data, select a proper algorithm for building a prediction model, and train your model to understand patterns of benign or malignant cells within the data. Once the model has been trained by going through data iteratively, it can be used to predict your new or unknown cell with a rather high accuracy. This is the power of machine learning. Machine learning impacts society in a very meaningful way. How do Amazon and Netflix recommend content and products for their users? They use machine learning. This is similar to how your friends might recommend a television show to you based on their knowledge of the types of shows you like to watch. How do you think banks make a decision when approving a loan application? They use machine learning to predict each applicant's default probability and then augment their decision to approve or deny the loan application based on that probability. How do telecommunication companies find how many of their customers will churn? They use demographic data to segment their customers and predict whether a customer will unsubscribe within the next month. Let's use computer vision as an example of how machine learning works. Assume you have a large collection of images of cats and dogs. You want to develop a software application to differentiate cats from dogs. The first thing you must do here is interpret the images as a progression of features. For example, does the image show the animal's eyes? If so, what is their size? Does it have ears? What about a tail? How many legs? Does it have wings? For machine learning, we had to painstakingly create rules to get computers to appear intelligent and detect the animals, but it was a failure. It needed a lot of rules, was too dependent on the current data set, and therefore unable to characterize unseen cases. Machine learning algorithms for computer vision have evolved to be able to identify dogs and cats in images. With machine learning, you can build a model that learns a set of distinguishing animal features from known examples and use them to infer the animal type automatically. Although machine learning applications in the modern world are increasing, humans are still in the mix. If an ML algorithm refuses a loan application, a banker wants to know why and initiates a follow-up. There are many other applications of machine learning that we see every day, such as virtual assistants like chatbots, logging into our phones using face recognition, or even playing computer games like chess. Each of these use different machine learning techniques and algorithms. In this video, You learned that machine learning is the subset of AI that uses algorithms and requires feature engineering by practitioners. Machine learning models learn using supervised, unsupervised, semi-supervised, and reinforcement learning. Machine learning consists of several techniques, namely classification, regression, clustering, association, anomaly detection, sequence mining, dimension reduction, and recommendation systems. Finally, you learned how machine learning is applied to predict diseases, analyze consumer behavior, and recognize images.
Welcome to Machine Learning Model Lifecycle. After watching this video, you'll be able to list the processes within the lifecycle of a machine learning product. Hello, my name is Isioma. I work as a machine learning engineer at a leading company. We sell machine learning solutions that enhance the user experience for people shopping for beauty products. Today, I'll walk you through a machine learning project from start to finish. Let's begin by looking at the processes in the lifecycle of a machine learning model. First, define the problem or state the situation. Next, move to data collection, then to data preparation, then to model development and evaluation, and finally, to model deployment. In reality, the model lifecycle is iterative, which means that we tend to go back and forth between these processes. For example, if you find some problems with your models that are deployed in production, you may need to go back to data collection, or even the problem definition step, and then reiterate the subsequent processes. Data collection and preparation is called the extract, transform, and load, or ETL process. The ETL process involves collecting data from various sources, then cleaning, transforming, and storing it into a new single place. The data is then accessible to the machine learning engineer, allowing them to perform tasks like building a machine learning model. In this video, you learned that the processes involved in a machine learning model lifecycle are problem definition, data collection, data preparation, model development and evaluation, and model deployment. Welcome to a day in the life of a machine learning engineer. After watching this video, you'll be able to describe the importance and requirements of each process in the lifecycle of a machine learning model, and name the processes that are more time-consuming than others. Now let's go through the lifecycle of a machine learning model in a project that I am currently working on. To help increase business revenue, I have been tasked with creating and deploying a model that recommends similar products to what the customer has already bought. I have worked together with a client to come up with an end user's pain point.
As a beauty product customer, I would like to receive recommendations for other products based on my purchase history so that I will be able to address my skincare needs and improve the overall health of my skin.
Defining the problem or stating the situation is very important because I want to make sure that the machine learning solution I am providing is aligned with the client's needs. Now that I understand the client's needs, the next step is to begin data collection. I should determine what kind of data the company has and identify the sources it will come from. This could be user data such as demographics, purchase history, and anything related to completed transactions. I can also get the product data, that is, the inventory of products and what they do, their ingredients, how popular they are, their customer ratings, and so on. Further, I may look at other data that includes information such as users saved products, liked products, search history, most visited products, and so on. Then, I will go ahead and do some major transforming by wrangling, aggregating, joining, merging, and mapping the data onto one central source. This reduces the need to deal with multiple databases every time we need to pull data. The next step in the process is data preparation. Most of the time, data from multiple sources will contain errors, different formatting, and missing data. This process overlaps with the data collection process as they can be done in tandem. The area of focus here is preparing a somewhat final version of the data. I will need to make sure that the data is cleaned to filter out irrelevant data, extreme values are removed to avoid influencing the data set, missing values are removed or randomly generated, depending on what the missing data may mean, and that each data column is in the proper format. For example, dates should be in date formats, and strings should be properly identified. I may also need to create additional features. For example, I may need to calculate the average duration between transactions for each user and find which products they buy the most. Or, I may need a feature that identifies what kind of skin issues each product targets and assign them to each user. I can create plots to visually identify patterns, validate the data based on information that the beauty product subject matter expert has given me, and do some correlation analysis to identify what variables or features are very important to the user's buying habits and needs. This is called exploratory data analysis. I can also identify how I plan on splitting the data for training and testing. For example, do I want to randomly split the data or use the most recent transaction as a test set? In this example, I decided to put the most recent transaction in the test set and make sure that there was at least one transaction by the same user in the training set. In the model development step, I will go ahead and build a machine learning model. Realistically, I try to leverage as many pre-existing frameworks and resources as possible, so I don't create anything from scratch. For this task, I will use a technique called content-based filtering. This technique finds the similarity between products based on product content. For example, if someone is using a cleanser with lots of water, it is likely that the user has dry skin and will want a moisturizer that is highly moisturizing as well. One of the steps I might take here is to create a similarity score of the products a user has purchased and rank them to other products. I might recommend the most similar product while bearing in mind that there may be other factors that could come into play. For example, I might notice that the user has searched for products without particular ingredients. So, I want to make sure that we are not recommending a product that they absolutely won't use. I would also use a technique called collaborative filtering that uses the user's data. Here, I am creating similarities between two users based on how they view a product. For example, I can create a similarity based on how two users rate their product. First, I group users into a bucket based on their characteristics. This could be age, region, and skin type, products the users rated, and or purchased. Then, I can take the average ratings for existing members and assume that the new user will be somewhere around the average, and recommend a product based on what others have rated highly. The final model will be a combination of the two techniques. After I am done building the model, I will go ahead and test that the model is performing well and that recommendations are representing what the users want. This is called the model evaluation step. The initial stages of model evaluation will involve me tuning the model and doing some testing on the data set I had kept earlier for testing. Once I am satisfied with the results, I will further evaluate the model by experimenting with the recommendations on a group of users and asking for their feedback. The feedback will include asking the group of users to rate the recommendations and collecting data on the number of people who clicked and bought the recommended products, along with any other necessary metrics. Now that I am done with building and testing, the model is ready to go to production. For this project, it will be part of the beauty product app and website. While this is the last step, I still need to track the deployed model's performance to make sure it continues to do the job that the business requires. Future iterations may include retraining the model based on new information in order to expand its capabilities. In this video, you learned that each of the steps of the machine learning model lifecycle is important to the success of the solution. After deployment, continuous monitoring and improving is required to ensure that the quality of the solution is maintained. Thank you for watching A Day in the Life of a Machine Learning Engineer.
For many years, data science has been called the sexiest job of the 21st century. But in recent years, it seems like there's a new job vying for that title, the AI engineer. So who even are these new kids on the block? Are they just data scientists in disguise? What's up, y'all? I'm Isaac Key, and I'm a former data scientist turned AI engineer at IBM. To answer these questions, I'm going to lay out 4 key areas in which the work of a data scientist differs from an AI engineer, specifically a generative AI engineer. But before I dive into these differences, we first have to understand more about what's happening in the industry. So traditionally, data scientists have always used AI models to do their analysis. So what's changed? Well, with the advent of generative AI, the boundaries of what AI can do are being pushed in ways that we've never seen before. And so these breakthroughs have been so groundbreaking that generative AI has split off into its own distinct field, and we call that AI engineering. Okay, so now that we understand the landscape, let's dive into the differences. The first area of difference lies in the use cases. So at a very high level, think of a data scientist as a data storyteller. They take massive amounts of messy real-world data, and they use mathematical models to translate this data into insights. On the other hand, think of an AI engineer as an AI system builder. They use foundation models to build generative AI systems that help to transform business processes. So since data scientists are fantastic storytellers, they use a lot of descriptive analytics to describe the past. One example of this is through what's called exploratory data analysis, or EDA, which is all about graphing the data and doing statistical inference. They can also do this through what's called clustering, which group similar data points based off of similar characteristics, such as, say, doing customer segmentation. Now, every good story has the reader trying to figure out what's going to come next, and that's where predictive use cases comes in. As opposed to a book, however, a data scientist does not have the end already written, so they have to use what are called machine learning models to make their predictions. An example of this is called regression models, which predict a numeric value such as, say, a temperature or a revenue. Another type of these models are classification models, which predict a categorical value such as a success or a failure. So, putting on the AI engineering hat now, one of the main use cases that AI engineers work on are called prescriptive use cases, which are all about choosing the best course of action. An example of this is a technique called decision optimization, which enables businesses to assess a set of possible actions and then choose the most optimal path based off a set of requirements or standards. Another example of a prescriptive use case is through creating what are called recommendation engines. As an example, this can involve suggesting targeted marketing campaigns for a select customer base. In addition to prescriptive use cases, there are also generative use cases, hence the name generative AI. Now, foundation models, which I will touch on more in a bit, enable the creation of what are called intelligent assistants, for example, a coding assistant or a digital advisor. They also enable the creation of chatbots, as an example, which enable conversational search through information retrieval and the summarization of various content. So after we have a use case identified, we need data. Now, people say that data is the new oil because, like oil, you have to search for and find the right data and then use the right processes to transform it into various products, which then power various processes. For a data scientist, the oil of choice is often structured data, aka tabular data. Do note that data scientists still work with unstructured data, but not as much as AI engineers. Now, these tables are often in the order of hundreds to hundreds of thousands of observations, and they require a lot of cleaning and pre-processing before the data can be modeled. Some of the cleaning involved, for example, involves removing outliers or joining and filtering on a new table, or even creating new features altogether. This clean data is then used to train various machine learning models. Now, on the other hand, an AI engineer, for them, the oil of choice is mainly unstructured data, such as text, images, videos, audio files, etc. Let's take a text-based foundation model called an LLM, or large language model, as an example. These models require anywhere between billions to trillions of tokens of text to be trained on, which is a lot larger scale compared to traditional machine learning models. This leads me to the next area of difference, which is the underlying models. So the data science toolbox consists of hundreds of different models and different algorithms that they can choose from. Due to the nature of these models, each different use case requires gathering a different data set and thus requires training a different model. And so as a result, the scope of these individual models is a lot more narrow, meaning that it's harder for them to generalize past the domain of data that they've been trained on. And generally speaking, these models are a lot smaller in size in terms of the number of parameters. They take less compute power to train and do inference, and they require less time to train, anywhere between seconds to hours. Now, on the other hand, the generative AI toolbox is a lot less cluttered, and it really only contains one type of model, and that is called the foundation model. Now, foundation models are revolutionary because they allow for one single type of model to generalize to a wide range of tasks without having to be retrained. Thus, their scope is called more wide. And due to the sophistication of these models, they are a lot larger in size, often billions of parameters. They require a lot more compute power to train. We're talking hundreds to thousands of GPUs. And they require a lot more training time. Now we're talking anywhere between weeks to months. Due to the differences in the intrinsic nature between traditional machine learning models and foundation models, this also means that the underlying processes and techniques that are used to develop solutions with these also differ. So a typical data science process will look something like this. You start off with a use case, and then from that use case, you pick the right data. Then after that data is prepared, you use it to train and validate a model using techniques such as feature engineering, cross-validation, or hyperparameter tuning, as an example. This model then is deployed at some endpoint, for example, in the cloud, to do real-time prediction and inference. Now, on the other hand, the generative AI process also starts off with a use case, but then we can skip directly to working with a pre-trained model. And what makes this possible is a phenomenon called AI democratization, which is a big fancy word that simply means making AI more widely accessible to everyday users. Some of the best foundation models out there are published to open source communities such as Hugging Face. And since these models are so generalizable and so powerful out of the box, they make it easy for developers to get started. AI engineers interact with these foundation models via natural language instructions to prompt them to do various tasks. And this process is known as prompt engineering. Now, prompt engineering can be used in conjunction with different frameworks to then build larger AI systems. An example of these frameworks include, as one, chaining different prompts together, or doing what's called parameter efficient fine-tuning, or PEFT, on domain-specific data, or doing retrieval augmented generation, aka RAG, to ground answers in truth, or even by creating autonomous agents to reason through very complex multi-step problems. So these are just a few of the examples of the building blocks that can be used to build larger AI applications. The last step is to then embed the AI in a larger system or workflow. This can take on the form of creating assistants or virtual agents building a larger application with a UI, or even doing some sort of automation. So, okay, let's take a step back and let's look at all the differences at a very high level. As we can see, the breakthroughs in generative AI underpin many of the differences in the use cases, data, models, and processes that data scientists and AI engineers work on. It's important to note that there is still overlap between the two fields. For example, data scientists will still work on prescriptive use cases, or an AI engineer will still work with structured data. Regardless of these differences, both of these fields are continuing to evolve at a blazing fast pace, with new research papers, new models, new tools coming out every single day. With data, AI, and a creative mind, really anything is possible with these. Thank you for tuning in. I hope this was helpful. Until next time, peace.
Welcome to Tools for Machine Learning. After watching this video, you will be able to explain why data is essential for machine learning models. You'll also be able to list common languages for machine learning. Finally, you'll be able to describe tools for data processing and analytics, data visualization, machine learning, deep learning, computer vision, natural language processing, or NLP, and generative artificial intelligence, or AI. Let's begin by asking the question, what is data? Data is a collection of raw facts, figures, or information used to draw insights, inform decisions, and fuel advanced technologies. Data is central to every machine learning algorithm and the source of all the information the algorithm uses to discover patterns and make predictions. Now, let's understand what are machine learning tools. Machine learning tools provide functionalities for machine learning pipelines, which include modules for data preprocessing and building, evaluating, optimizing, and implementing machine learning models. These tools use algorithms to simplify complex tasks, such as handling big data, conducting statistical analyses, and making predictions. A good example is the Pandas library, used for data manipulation and analysis. Another example is the Scikit-learn library, which provides a wide range of supervised and unsupervised learning algorithms for linear regression. A machine learning programming language is a programming language for building machine learning models and decoding the hidden patterns in data. Python is a widely used language due to its extensive collection of libraries for analyzing and processing data and its ease in developing machine learning models. R is another popular language for statistical learning that also contains many libraries for data exploration and machine learning. Here are some other common languages. Julia is a high-performance language with parallel and distributed numerical computing support used by researchers. Scala is a scalable, widely used language for processing big data and building machine learning pipelines. Java is a multi-purpose language that supports scalable machine learning applications deployed in production. And JavaScript is used to run machine learning models in web browsers to serve client-side applications. Machine learning tools serve several purposes. You can use them to store and retrieve data, work with plots, graphs, and dashboards, explore, visually inspect, and clean data, and prepare data for developing machine learning models. These tools can be divided into specific categories, as shown here. Data processing and analytics tools process, store, and interact with data to serve machine learning models. Here are some examples. PostgreSQL is a powerful open-sourced object relational database system based on SQL, a language designed for storing, manipulating, and retrieving data in databases. Hadoop is an open-source, highly scalable disk-based solution for storing and batch processing massive data. Spark is a distributed in-memory data processing framework for real-time big data processing. It supports data frames and SQL and is faster and easier to use than Hadoop. Apache Kafka is a distributed streaming platform for building big data pipelines and running real-time analytics. Pandas is a popular Python library for exploring and wrangling data. Central to Pandas is the data frame, a tabular data structure for cleaning and transforming structured data. NumPy is a Python library that provides comprehensive mathematical functions, random number generators, and linear algebra routines for distributed and graphics processing unit or GPU-based computing platforms. Data visualization tools help you understand and visualize the structure of your data. Let's look at some commonly used tools. Matplotlib is an extensive foundational library for generating customizable plots and interactive visualizations. Seaborn is a library based on Matplotlib. It provides a high-level interface for drawing attractive and informative statistical graphics. ggplot2 is an open-source data visualization package in R. It allows you to build and add elements to your graphics in layers. Tableau is a business intelligence tool for interactive data visualization dashboards. Machine learning tools are used to create and tune your machine learning models. Several open-source Python libraries form a widely used ecosystem for machine learning. NumPy provides foundational machine learning support with efficient numerical computations on large, multidimensional data arrays. Pandas is used for data analysis, visualization, cleaning, and preparing data for machine learning. SciPy, built on NumPy, is used for scientific computing and has modules for optimization, integration, linear regression, and more. Scikit-learn is used for building classical machine learning models, offering a full suite of classification, regression, clustering, and dimensionality reduction algorithms. It's built on NumPy, SciPy, and Matplotlib. Deep learning tools are frameworks for designing, training, and testing neural network-based machine learning models. For deep learning, there are several popular libraries available. TensorFlow is an open-source library for numerical computing and large-scale machine learning. Keras is an easy-to-use deep learning library for implementing neural networks. Theano is for efficiently defining, optimizing, and evaluating mathematical expressions involving arrays. PyTorch is an open-source library for deep learning applications in computer vision and NLP. It also allows experimentation to test ideas. Computer vision tools are used for tasks such as object detection, image classification, facial recognitions, and image segmentation. All the deep learning tools can be tailored to computer vision applications. Let's look at some examples. OpenCV, or Open Source Computer Vision Library, is a library for real-time computer vision applications such as object detection, image classification, and augmented reality. Scikit-image, built on SciPy and compatible with Pandas, offers image processing algorithms such as filters, segmentation, feature extraction, and morphological operations. Torch Vision, part of the PyTorch project, consists of popular datasets, image loading, pre-trained deep learning architectures, and common image transformations for computer vision. NLP tools help developers and data scientists build applications that understand, interpret, and generate human language. Let's look at some popular NLP tools. The Natural Language Toolkit, or NLTK, is a comprehensive library that offers text processing, tokenization, and stemming tools. TextBlob is a library for tasks like part-of-speech tagging, noun phrase extraction, sentiment analysis, and translation. Stanza is an NLP library from the Stanford NLP group with accurate pre-trained models for many NLP tasks, including part-of-speech tagging, named entity recognition, and dependency parsing. Generative AI tools leverage AI to generate new content based on input data or prompts, such as text, images, music, code, or other media. Here are some examples. Hugging Face Transformers is a powerful library of transformer models for NLP tasks, such as text generation, language translation, and sentiment analysis. ChatGPT is a powerful language model used for text generation, building chatbots, and other NLP tasks. DALL-E is a tool from OpenAI for generating images from textual descriptions. PyTorch uses deep learning to create generative models, such as generative adversarial networks, or GANs, and transformers for text and image generation. In this video, you learned that data is central to every machine learning algorithm. Machine learning tools simplify complex tasks and provide functionalities for machine learning pipelines. A machine learning programming language is used to build machine learning models and decode data patterns. Some commonly used languages are Python, R, Julia, Scala, Java, and JavaScript. Finally, you explored the tools used for data processing and analytics, data visualization, machine learning, deep learning, computer vision, NLP, and AI. Welcome to Scikit-learn Machine Learning Ecosystem. After watching this video, you will be able to describe the machine learning ecosystem. You will also be able to explain the features of the Scikit-learn library and how it works. Imagine you developed a music streaming app that allows users to play and download music, share music files, and create playlists. To increase your app's user base, you collect information on your users' listening habits, such as what songs they play, how long they listen to songs, and which songs they skip. Once you've collected the information, you want to normalize it by finding inconsistent data, missing values, and outliers. Machine learning tools can generate this type of information. They are useful for data collection, pre-processing, model training, model evaluation, model deployment, and monitoring. The machine learning or ML ecosystem refers to the interconnected tools, frameworks, libraries, platforms, and processes that support developing, deploying, and managing machine learning models. Python offers a wide variety of tools and libraries for machine learning. Several open-sourced Python libraries comprise one of the most widely used ecosystems for machine learning. NumPy provides foundational machine learning support with its efficient numerical computations on large multidimensional data arrays. Pandas, built on NumPy and matplotlib, is used for data analysis, visualization, cleaning, and preparing data for machine learning. Pandas use versatile arrays called data frames to handle data. SciPy, built on NumPy, is used for scientific computing and has modules for optimization, integration, linear regression, and more. Matplotlib is built on NumPy and has an extensive, highly customizable set of visualization tools. Scikit-learn, built on NumPy, SciPy, and Matplotlib, is used for building classical machine learning models. Let's take a closer look at Scikit-learn. Scikit-learn is a free machine learning library for the Python programming language. It has a wide, up-to-date selection of classification, regression, clustering, and dimensionality reduction algorithms. It's designed to work with the Python numerical and scientific libraries NumPy and SciPy. It has excellent documentation and a large community support network. Scikit-learn is constantly evolving with contributions from a community of thousands and is exceeded only by pandas. Implementing machine learning models with Scikit-learn is easy, with just a few lines of Python code. Most of the tasks that need to be done in a machine learning pipeline are already implemented in Scikit-learn, including data preprocessing tasks like data cleaning, scaling, feature selection, and feature extraction, train or test splitting, model setup and fitting, hyperparameter tuning with cross-validation, prediction, evaluation, and exporting the model to be used in production. Here's an example of a basic machine learning workflow using the Scikit-learn library. Consider a dataset X and a target variable Y, both stored as NumPy arrays. Scikit-learn's preprocessing package provides several common utility functions and transformer classes to help you prepare data for modeling. For instance, this first code block scales your data by standardizing it. In supervised learning, you want to split your dataset into train and test sets to train your model and then test the model's accuracy separately. Scikit-learn can split arrays and matrices into random train and test subsets for you in one line of code. Here, 33% of the data is reserved for testing. Next, you can instantiate a classifier model using a support vector classification algorithm. This line of code generates a classification model object called CLIF and initializes its parameters, gamma and c. After initializing your model CLIF, you can train your model on the training data. The CLIF model learns to predict the classes for unknown cases by passing the training set to the fit method. Then you can use the test data to generate predictions. The result tells you the predicted class for each observation in the test set. You can also use different metrics to evaluate your model accuracy, such as a confusion matrix to compare the predicted and actual labels for the test set. And finally, you can save your model as a pickle file and retrieve it whenever you like. In this video, you have learned that a machine learning ecosystem refers to the interconnected tools, frameworks, libraries, platforms, and processes that support developing, deploying, and managing machine learning models. It uses several Python tools and libraries, such as NumPy, Pandas, SciPy, Matplotlib, and Scikit-learn. Scikit-learn is a free machine learning library for Python that uses classification, regression, clustering, and dimensionality reduction algorithms. Most tasks required in a machine learning pipeline are already implemented in Scikit-learn. Finally, you learn the basic machine learning workflow using the Scikit-learn library. Welcome to Introduction to Regression. After watching this video, you will be able to define regression, compare simple and multiple regression, explain applications of regression, Regression is a type of supervised learning model. It models a relationship between a continuous target variable and explanatory features. Consider this dataset related to CO2 emissions from different cars. The features in this dataset include engine size, number of cylinders, fuel consumption, and CO2 emissions from various automobile models. Given this dataset, is it possible to predict the CO2 emission of a new car from the listed features? The answer is yes. Using potentially predictive features, you can use regression to predict a continuous value, such as CO2 emissions. Let's consider the previous dataset comprising some features in past cars. Then, from that data, a model can be trained to estimate the CO2 emissions of each car. Let's use regression to build such a predictive model. Then, the model is used to predict the expected CO2 emission for a new or hypothetical car. There are several types of regression. Deciding which one to use depends on the data you have for the dependent variable and the type of model that provides the best fit. In this video, we'll discuss the following two types of regression models: simple regression and multiple regression. Simple regression is when a single independent variable estimates a dependent variable. Simple regression can be linear or nonlinear. For example, predicting CO2 emission using the variable engine size. Simple linear regression imposes a linear relationship between the dependent and independent variables. Similarly, nonlinear regression creates a nonlinear relationship between those variables. When more than one independent variable is present, the process is called multiple regression. The distinctions between linear and nonlinear relationships apply to simple and multiple regression. For example, predicting CO2 emission using engine size and the number of cylinders in any given car. Again, depending on the relation between dependent and independent variables, it can be either linear or nonlinear regression. Let's examine some sample applications of regression. Essentially, we use regression when we want to estimate a continuous value. For instance, one of the applications of regression analysis could be in the area of sales forecasting. You can predict a salesperson's yearly sales from independent variables, such as customers, number of leads, and order history. Regression analysis can predict the price of a house in an area based on its size, number of bedrooms, and so on. You can use regression analysis to predict when an automobile or an industrial machine will require maintenance rather than waiting for it to fail. You can even use it to predict employment income from independent variables, such as hours of work, education, occupation, sex, age, years of experience, and so on. Indeed, you could find many examples of the usefulness of regression analysis in these and many other fields or domains, such as finance, healthcare, and retail. Let's examine additional sample applications of regression. You can use regression to estimate the rainfall in a region based on meteorological factors, such as temperature, humidity, wind speed, and air pressure. It can also be used in the field of environmental protection, for example, to determine the probability and severity of wildfires. In public health, you can use regression analysis to predict the spread of infectious diseases. You can even use it to estimate the likelihood of developing diseases, such as diabetes, heart disease, or cancer, based on patient data. There are many regression algorithms. Each algorithm is important in the appropriate context and suited to specific conditions. Linear and polynomial regression are classical statistical modeling methods, while random forest and XGBoost are modern machine learning regression models. Other modern regression algorithms include k-nearest neighbors, support vector machines, and neural networks. In this video, you learned regression is a machine learning technique that models a relationship between a continuous target variable and explanatory features. Simple regression is when a single independent variable estimates a dependent variable. This regression can be linear or nonlinear. When more than one independent variable is present, the process is called multiple regression. There are many applications of regression. You can use it to forecast sales, predict maintenance expenses, estimate rainfall, and spread of infectious disease. Welcome to this video on Introduction to Simple Linear Regression. After watching this video, you will be able to describe simple linear regression and explain how simple linear regression works. Linear regression models a linear relationship between a continuous target variable and explanatory features. Consider this dataset related to CO2 emissions from different cars. The dataset features engine size, number of cylinders, fuel consumption, and CO2 emissions from various cars. Given this dataset, linear regression can be used to predict a continuous value, such as CO2 emissions of a car. In simple linear regression, a single independent variable estimates the dependent variable. For example, in our dataset, CO2 emission is predicted using the engine size variable. Let's consider the same dataset again. Let's plot engine size as an independent variable and CO2 emissions as the target value that we want to predict. A scatter plot clearly shows the correlation between variables where changes in one variable explain or possibly cause changes in the other variable. With simple linear regression, you can determine a best fit line through the data. As engine size increases, so does CO2 emissions, and the relationship is approximately linear. You can use simple linear regression to predict the emission of an unknown car. For example, the predicted emission for a sample car with an engine size of 2.4 is 214. You can predict the target value CO2 emissions represented as the response variable y hat. The independent variable, which in this case is engine size, is represented by the single predictor variable x1. The model is represented as the equation of a line here. Y hat is the predicted response expressed in terms of x1 using a y-intercept, theta 0, and a slope, theta 1. Theta 0 and theta 1 are called the coefficients of the linear regression model, selected by the linear regression algorithm to determine a best fit line. Let's consider some new data points and check how well they align with the regression line. Given a car with engine size x1 equals 5.4, its actual CO2 emission is 50, while its predicted emission is y hat equals 340. Comparing the actual value to the predicted one, there's a 90-unit discrepancy. The residual error is the vertical distance from the data point to the fitted regression line. The average of all residual errors measures how poorly the regression line fits the data. Mathematically, it can be shown by the equation mean squared error, shown as MSE. Linear regression aims to find the line for minimizing the mean of all these residual errors. This form of regression is commonly known as ordinary least squares regression, or OLS regression. We can use two formulas to calculate the coefficients theta 0 and theta 1 of the linear regression model. The solution was derived independently by the mathematicians Gauss and Legendre in the early 1800s. It requires that we calculate the means, y bar and x bar, of the independent and dependent variables. The xi and yi in the equation for theta 1 refer to the ith values of x and y. Here, you can calculate the x bar as 3.0 and the y bar as 226.2. Then, going through the calculations, you'll find that theta 1 equals 39. You can use this result to calculate the first parameter line intercept as 125.7. So, these are the two parameters for the line, where theta 0 is also called the bias coefficient, and theta 1 is the coefficient for the CO2 emission column. Given the parameters of the linear equation, making a prediction is as simple as solving the equation for a particular input value. For example, you can predict the CO2 emission from engine size for the automobile in record number 9 using the following equation. For an engine size of 2.4, we can predict that the CO2 emission of the car would be 214. The OLS regression method is helpful because it's easy to understand and interpret. The method doesn't require any tuning, and its solution is just a calculation. This also makes OLS regression fast, especially for smaller data sets. On the other hand, a linear model may be far too simplistic to capture complexity, such as a nonlinear relationship in the data. Outliers can greatly reduce its accuracy, giving them far too much weight in the calculations. In this video, we looked at several use cases of simple linear regression. We learned how to predict a continuous value, such as a car's CO2 emissions. In simple linear regression, a single independent variable estimates the dependent variable. We also learned how to determine the best fit line through a chart showing regression values. We learned about the concept of mean squared error, or MSE, which measures how poorly the regression line fits the data. Linear regression aims to find the line for minimizing the mean of all these residual errors. This form of regression is commonly known as ordinary least squares regression, or OLS regression. The OLS regression method is useful because it's easy to understand and interpret. However, outliers can greatly reduce its accuracy, giving them far too much weight in the calculations. Welcome to this video on Introduction to Multiple Linear Regression. After watching this video, you will be able to describe multiple linear regression, compare multiple linear regression and simple linear regression, and list the pitfalls of multiple linear regression. Multiple linear regression is an extension of the simple linear regression model. It uses two or more independent variables to estimate a dependent variable. Mathematically, the multiple regression model is a linear combination of the form y hat equals theta 0 plus theta 1 x1, where the x1 are the feature vectors that can be represented as a matrix X that includes a constant value of 1 in the first entry to account for the bias or intercept term theta underscore 0, and the thetas are the unknown weights, which can be represented as matrix theta. Let's consider the data set in this table. Multiple linear regression can be used to measure the strength of each independent variable's effect on a dependent variable. You can predict the CO2 emission of a motor car from features like engine size, number of cylinders, and fuel consumption by forming a linear combination of the features using trained weights, theta I. You can use the trained model to predict the expected CO2 emission of an unknown case, such as record number 9. Multiple linear regression results in a better model than using a simple linear regression. However, adding too many variables can cause your model to overfit or essentially memorize the training data, making it a poor predictor for unseen observations. To improve prediction, categorical independent variables can be incorporated into a regression model by converting them into numerical variables. For example, given a binary variable such as car type, the code 0 for manual and 1 for automatic cars can be substituted to make it numerical. For a categorical variable with more than 2 classes, you can opt to transform it into new Boolean features, one for each class. Multiple linear regression has applications in every industry. It is widely used in the education sector to predict outcomes and explain relationships between variables. For example, do revision time, test anxiety, lecture attendance, and gender affect student exam performance? Multiple linear regression can also be used to predict the impact of changes in what-if scenarios. What-if scenarios involve hypothetical changes to one or more of your model's input features to see the predicted outcome. For example, suppose you were reviewing a person's health data. In that case, multiple linear regression might be able to tell you how much that person's blood pressure would rise or fall for every change in a patient's body mass index, BMI. The what-if scenario can sometimes provide inaccurate findings in the following situations. You might consider impossible scenarios for your model to obtain predictions. You might extrapolate scenarios that are too distant from the realm of data it was trained on. Your model might depend on more than one variable amongst a group of correlated or collinear variables. When 2 variables are correlated, they are no longer independent variables because they are predictors of each other. They are collinear. You can perform a what-if scenario with a linear regression model by changing a single variable while holding all other variables constant. However, if the variable is correlated with another feature, then this is not feasible because the other variable must also change realistically. The solution for avoiding pitfalls from correlated variables is to remove any redundant variables from the regression analyses. To build your multiple regression model, you must select your variables using a balanced approach, considering uncorrelated variables, which are most understood, controllable, and most correlated with the target. Multiple linear regression assigns a relative importance to each feature. Imagine you are predicting CO2 emission, or Y, from other variables for the automobile in record number 9. Once you find the parameters, you can plug them into the linear model equation model. For example, let's use theta 0 equals 125, theta 1 equals 6.2, theta 2 equals 14, and so on. If we map these values to our data set, we can rewrite the linear model as CO2 emission equals 125 plus 6.2 multiplied by engine size plus 14 multiplied by cylinder, and so on. Now, let's plug in the 9th row of R and calculate the CO2 emissions for a car with a 2.4-liter engine. So CO2 emission equals 125 plus 6.2 times 2.4 plus 14 times 4, and so on. We can predict the CO2 emission for this specific car will be 214.1. For a simple linear regression, where there is only one feature vector, the regression in the equation defines a line. For multiple linear regression using 2 features, the solution describes a plane. Beyond 2 dimensions, it describes a hyperplane. Like with simple linear regression, the values in the weight vector theta can be determined by minimizing the mean square prediction error. Given a set of parameters, consider a linear model based on the linear combination of the parameters with the features. You can measure the residual error for each car in the data set as the difference between its true CO2 emission value and the value predicted by the model. For example, if the model predicts 140 as the value for the first car in the dataset, using the actual value of 196, you can see the residual error is 196 minus 140, or 56. The average of all the residual errors indicates how poorly the model predicts the actual values. This information is called the mean squared error, or MSE. MSE is not the only way to expose the error of a linear model. However, it is the most popular. With this metric, the best model for the dataset is the one with the least squared error. The factor of 1/n in the MSE equation isn't necessary to include to minimize the error, so this method is called least squares linear regression. So, multiple linear regression aims to minimize the MSE equation by finding the best parameters. There are many ways to estimate the value of these coefficients. However, ordinary least squares and an optimization approach are the most common methods. Ordinary least squares estimate the values of the coefficients by minimizing the mean squared error. This approach uses the data as a matrix and uses linear algebra operations to calculate the optimal values for theta. Another option is to use an optimization algorithm to find the best parameters. That is, you can use a process of optimizing the coefficients by iteratively minimizing the model's error on your training data. For example, you can use the gradient descent method, which starts the optimization with random values for each coefficient. Gradient descent is a good approach if you have a large dataset. Multiple linear regression is an extension of the simple linear regression model. It uses two or more independent variables to estimate a dependent variable. It is widely used in the education sector to predict outcomes and explain relationships between variables. Multiple linear regression can also be used to predict the impact of changes in what-if scenarios. Adding too many variables can cause your model to overfit or essentially memorize the training data, making it a poor predictor for unseen observations. To build your multiple regression model, you must select your variables using a balanced approach, considering uncorrelated variables, which are most understood, controllable, and most correlated with the target. There are many ways to estimate the parameters for multiple linear regression. However, ordinary least squares and an optimization with random values approach are the most common methods. In this video, you learned how multiple linear regression results in a better model than using a simple linear regression. Welcome to Introduction to Polynomial and Nonlinear Regression. After watching this video, you will be able to describe polynomial regression, describe nonlinear regression, and demonstrate applications of nonlinear regression. Nonlinear regression is a statistical method for modeling the relationship between a dependent variable and one or more independent variables, where the relationship is represented by a nonlinear equation. This equation could be polynomial, exponential, logarithmic, or any other function that does not use linear parameters. Nonlinear regression is useful when there is a complex relationship between variables that cannot be captured through a straight line. For instance, you would use nonlinear regression when you are using a dataset that follows an exponential growth pattern. Let's consider the two charts here. The red line through the data in the left chart is a reasonable fit. However, with real-world data, the relationship between your input and target variables is rarely linear. More commonly, your data has a background trend that follows a smoothed curve rather than a straight line, like in the right chart. Clearly, a smooth nonlinear curve does a better job at approximating data than the straight line. The straight line underfits the data. You can use many kinds of nonlinear regression methods to model your data set. Polynomial regression uses an ordinary linear regression to indirectly fit your data to polynomial expressions of the features rather than the features themselves. Nonlinear regression follows the same idea, but bases its inputs on functions of the given features, such as the logarithm or exponential of the features. Nonlinear regression doesn't necessarily reduce to linear regression like polynomial regression does. In this chart, you can see linear, quadratic, and cubic regression curves that fit the patterns in the data quite well, and this approach can go on and on to polynomials of arbitrary degree. We can call all of these polynomial regression, where the relationship between the independent variable x and the dependent variable y is modeled as an nth degree polynomial in x. Consider this polynomial regression example where a good candidate for a fit is a cubic or third degree polynomial given by y equals theta 0 plus theta 1x plus theta 2x squared plus theta 3x cubed. Here, the thetas are parameters to be estimated that best fit the underlying data by introducing new variables as x_1 equals x underscore2 equals x to the power of 2, and x_3 equals x to the power of 3. The model can now be expressed as a linear combination of the new variables as y equals theta 0 plus theta 1x1 plus theta 2x2 plus theta 3x3. Because the resulting model has been linearized, you can simply use ordinary multiple linear regression to find the best fit parameters. Given any finite sets of points, it's always possible to find a polynomial of sufficiently high degree that will pass through every point. Such a perfect fit amounts to overfitting as seen in this chart. The polynomial regression model memorizes everything, including any random noise or large variations, rather than understanding the underlying patterns. It's important to pick a regression that fits the data well without overfitting. You don't need to capture every fine detail, just the trend. Polynomial regression is a special form of nonlinear regression. It expresses a nonlinear dependence on the input features, but it has a linear dependence on the regression coefficients because it can be transformed into a linear regression problem. It is often simply called linear regression. In contrast, there are many real-world complex nonlinear relationships that can't be modeled as polynomials. Such common examples of nonlinear regression include exponential or compound growth. For example, how investments grow with compound interest rates. Logarithmic. For example, law of diminishing returns, how incremental gains in productivity or profit can reduce as investment in a production factor, such as labor increases. Periodicity. For example, sinusoidal seasonal variations in a quantity, such as monthly rainfall or temperature. Let's consider this data corresponding to China's gross domestic product, or GDP, from 1960 to 2014. Each row provides China's annual GDP in US dollars for the year. The scatter plot displays a strong dependence of GDP on time, but the relationship is nonlinear. As you can see, GDP increases over time, and the rate of this growth also increases. This increasing growth rate is characteristic of exponential growth. A reasonable regression model then uses an exponential function, like y hat equals theta 0 plus theta 1 ex. Consider the following simulated example involving human productivity as a function of the number of consecutive hours worked. Working more hours per day on average increases your productivity. However, after a reasonable limit, say 6 hours of work, each additional work hour generates less productivity per hour than the previous hour. This is an example of diminishing returns. The first 6 hours of the model show a linear increase in cumulative productivity, but then the returns slow down and become logarithmic. There are many methods to determine what kind of regression model you need. One technique is to visually determine whether the relation is linear or nonlinear. Analyzing scatter plots of your target variable against each input variable can reveal patterns in the dependencies. Try to express these patterns as mathematical functions and determine if they're linear, exponential, logarithmic, or sinusoidal. Generate models and analyze your results. There's always a chance that your data might have no relationship with your target. You can visually interpret your model's errors by plotting its predictions against the actual target values. How can you find an optimal nonlinear model? If you have a mathematical expression for your proposed model, you can use an optimization technique like gradient descent to find optimal parameters. Otherwise, if you haven't decided on a specific regression model, you can select amongst many machine learning models. Some options include regression trees, random forests, neural networks, support vector machines, gradient boosting machines, k-nearest neighbors. Nonlinear regression uses polynomial, exponential, logarithmic equations to model data. It is used when the relationship between variables cannot be captured through a straight line. In this video, you learned how you can use polynomial regression to fit your data to polynomial expressions of the features. The polynomial regression model memorizes everything, including any random noise or large variations, rather than understanding the underlying patterns. There are many real-world complex nonlinear relationships that can't be modeled as polynomials. Some common examples of nonlinear regression include exponential or compound growth, logarithmic, and periodicity. There are many methods to determine what kind of regression model you need. You can analyze scatter plots of your target variable against each input variable to reveal patterns in the dependencies. To find an optimal nonlinear model, you can select amongst many machine learning models, such as regression trees, random forests, and k-nearest neighbors. Welcome to Introduction to Logistic Regression. After watching this video, you will be able to describe the machine learning method of logistic regression and explain how it is used. Logistic regression is a statistical modeling technique that predicts the probability of an observation belonging to one or two classes, such as true or false. In machine learning, logistic regression refers to a binary classifier based on statistical logistic regression. By choosing a threshold probability, the probability predictor becomes a binary classifier simply by assigning each observation to one class if its probability is greater than the threshold, and to the other class if its probability is less than the threshold. Let's understand when logistic regression is a good choice. First, when the target in your data is binary, indicated as 0 or 1. Second, when you need the probability of an outcome, like the probability of a customer buying a product. If the data is linearly separable, the decision boundary of logistic regression is a line, a plane, or a hyperplane. Example, theta 0 plus theta 1 x 1 plus theta 2 x 2 is greater than 0. Third, when you want to understand the impact of an independent feature, it allows you to select the best features based on the size of their model coefficients or weights. Logistic regression is both a probability predictor and a binary classifier. For example, you can use it to predict the probability that a person will have a heart attack within a specified time period based on knowledge of the person's age, sex, and body mass index. Chance that a specific condition or disease, such as diabetes, might appear based on observed characteristics of that patient, such as weight, height, blood pressure, and results of various blood tests, and so on. Likelihood that a customer of a subscription-based service will halt its subscription, probability of failure of a given process, system, or product, and likelihood of a homeowner defaulting on a mortgage. Consider a telecommunication dataset that you'd like to analyze to predict which customers might leave next month. The dataset comprises historical customer data, where each row represents one customer. The data includes information about services that each customer has signed up for, customer account information, demographic information like gender and age range, and customers who've churned or left within the last month. Here, the dependent variable column is called churn. In logistics regression, you can use one or more of these features to predict whether customers will churn. Logistic regression can predict the class, y hat, of each customer by considering the predicted probability, p hat, that the customer will churn. Here, p hat is the predicted probability that the class, y is 1, given the data, x. Suppose the goal is to predict customer churn based on their age. You have a feature, age, denoted as x, and a binary target, variable churn, denoted as y, with two classes, yes and no, represented by binary values 1 and 0. Graphically, you can represent the data with a scatter plot, where class 0 is denoted in red and class 1 in blue. With linear regression, you can fit a line through the data represented as y hat equals theta 0 plus theta 1 x1. This line has two parameters, where theta 0 is the y-intercept of the line and theta 1 is its slope. Theta 1 is also called the weight vector, or confidence of the equation. One problem is that the prediction's value y hat increases indefinitely with age because the line goes on forever. Obviously, you cannot use linear regression directly to predict churn. Somehow, the predicted values need to be contained within the range 0 to 1. One way to keep the predicted values within the range of 0 to 1 is to use a threshold, like 0.5, to differentiate the classes. You can write a rule to allow you to separate class 0 from class 1. If the value of y hat is less than 0.5, then the class is 0. Otherwise, the class is 1. Notice that in the step function, no matter how big the value is, as long as it's greater than 0.5, it simply equals 1. And regardless of how negative the value y hat is, the output is 0 if it is less than 0.5. In other words, there is no difference between a customer 20 years old and 100 years old. The outcome would be 1. Wouldn't it be nice to use a smoother line that would project these values between 0 and 1? Indeed, the existing method doesn't provide the probability of a customer belonging to a class, which is the goal. Consider the sigmoid function, sigma of x, also known as the logit function, defined as 1 over the sum of 1 and e to the minus x. This graph shows that for x equals 0, the sigmoid function is 0.5. As x grows, the sigmoid function approaches 1, and as x becomes more negative, the sigmoid approaches 0. This means that the sigmoid function can take any continuous function of x and continuously compress it within the range 0, 1. It defines a probability. Now, the model is sigma of y hat, which represents the probability, p hat, and that the output is 1 given x. Thus, you can determine the chance that an observation belongs to either class. To assign the class to the observation, simply define a threshold like 0.5 and assign the observation to 1 if its probability is greater than 0.5 and 0 otherwise. This threshold is known as a decision boundary. What is the output of the customer churn model when we use the sigmoid function? The churn probability is denoted as the probability that y is 1 given the data x. Notice that the probability that the customer won't churn is 1 minus the churn probability, as the two probabilities must add to 1. For example, suppose the probability of a customer staying with the company can be shown as the probability of churn given a customer's income and age, which could be 0.8. Then, the probability of the same customer staying is 1 minus 0.8, which is 0.2. In this video, you learned that in machine learning, logistic regression refers to a binary classifier based on statistical logistic regression, or probability predictor. Logistic regression is a good choice for a binary target, probabilistic results, and understanding the impact of a feature. You also learned that logistics regression is both a probability predictor and a binary classifier. The goal of logistic regression is to build a model to predict the class by considering the predicted probability. Welcome to training a logistic regression model. After watching this video, you will be able to describe how to train a logistic regression model. You will also be able to explain the features of the gradient descent and stochastic gradient descent method. In logistical regression training, you look for the best parameters that map the input features to the target outcomes. The objective is to predict classes with minimal error. The training process seeks to find a set of parameters, also known as theta, that minimizes the cost function. The process of training a logistical regression model comprises several steps. First, you have to choose a starting set of parameters called theta. This can be a random choice. You then predict the probability that the class is 1 for each observation of your data. The next step is to measure the error between the predicted classes and the actual classes. This error is called a cost function. You then determine a new theta that reduces the prediction error. Finally, you need to repeat the process until you reach a small enough value for the log loss, or a specified maximum number of iterations. Next, let's understand optimal logistic regression. The process of creating a decision boundary by combining a linear model y hat in terms of parameters theta with the sigmoid function yields a binary classification model, or what might be called a preliminary logistic regression. The model is called preliminary because it's not necessarily the best logistic regression model. The best logistic regression model can only be achieved after the first pass. The model parameters, theta, need to be found. An optimization step finds the best parameters. To achieve optimization, you need a metric that determines the model's goodness of fit for a given set of parameters. The metric for optimizing logistic regression is a cost function called log loss, which needs to be minimized. Log loss is a cost function that measures how well the predicted probabilities, p hat I, match the actual classes yi. Logistic regression seeks to minimize this cost function. Here, I refers to the ith observation of the data, which is n rows. Log loss is defined as minus the average over I of two terms. The actual class times the logarithm of the predicted probability that the class is 1 plus 1 minus the actual class times the log of the probability that the class is 0. The negative sign exists because the logarithm is negative for arguments between 0 and 1. Log loss favors confident classifications that are correct. For instance, when the predicted probability of class 1 is high and correct, p hat I is close to 1 for an observation, and yi is equal to 1. You can convince yourself by inspecting the formula that the log loss is small. Indeed, the first term vanishes because the log term tends to 0 as the probability approaches 1, while the second term vanishes because the factor 1 minus yi is 0. In this way, log loss penalizes confident, incorrect predictions. When the predicted probability of class 0 is high and incorrect, that is, when p hat is close to 1 for an observation, and the actual class is 0, the log loss is very large. There are various ways to stop iterations, but essentially you stop training when your model's log loss is satisfactory. Different techniques can be used to change the values of theta, and one of the most popular methods is gradient descent. Gradient descent is a clever iterative approach to finding the minimum of a function. It adjusts the parameter values in the direction of the steepest descent using the derivative of the log loss function. Gradient descent depends on a specified learning rate, which controls how far it's allowed to step the parameters on each iteration. The main objectives of gradient descent is to change the parameter values and find a path to the optimal parameters to minimize the cost function. Consider the plot, which simulates a parabolic log loss cost function of the trial parameters theta1, theta2. This surface represents the error for different values of parameters. The gradient of the surface points in the direction of the steepest ascent. Thus, the negative of the gradient points in the direction of the steepest descent. Hence the name, gradient descent. The steeper the slope, the greater the magnitude of the gradient, and thus, the greater the step toward the minimum. You can control the size of each step by scaling the gradient by a factor called the learning rate. As the lowest point is reached, the slope diminishes to 0. This lowest point of the path occurs at the optimum theta1, theta2. Let's explore some additional features of gradient descent. The gradient of the cost function is calculated over the entire data set on each iteration. When the data set is large, gradient descent becomes very slow. You could try speeding up the convergence by increasing the learning rate, but convergence becomes less likely as the steps might be too big to notice the minima. Instead of using the whole, the cost function gradient can be approximated by choosing a random subset of the data to calculate it on. A variation of the gradient descent algorithm is stochastic gradient descent, or SGD. It's faster, but can be less accurate. It uses a random subset of training data and scales well. SGD is more likely to overlook local minima and find global minima of the cost function. It converges quickly toward a global minimum, but can wander around it for some time. The convergence can be improved by slowing down as the algorithm gets closer to a global minimum. You can home in on the minimum by decreasing the learning rate as you get closer, or you can gradually increase the size of the random data sample used to calculate the gradient of the cost function. In this video, you learned that the objective of logistical regression training is to predict classes with minimal error. The training process consists of key steps created to find a set of parameters, or theta, that minimize the cost function. An optimization step is used to find the best parameters. The metric for optimizing logistic regression is a cost function called log loss, which needs to be minimized. Log loss favors confident classifications that are correct and penalizes confident, incorrect predictions. Gradient descent is a clever iterative approach to finding the minimum of a function. Stochastic gradient descent is a scalable variation of the gradient descent algorithm, which uses a random subset of training data. Welcome to this video on classification. After watching this video, you will be able to describe the classification method of supervised learning, discuss the applications and use cases of classification, list the different classification algorithms, and explain how to make multi-class predictions. Classification is a supervised machine learning, or ML method, that uses fully trained models to predict labels on new data. The labels in classification form a categorical variable with discrete values. Supervised learning aims to understand data in the correct context when answering a specific question. This ensures data accuracy when making predictions. As data is input into the model adjusts the data to fit the algorithm and classifies it accordingly, defining the input and the predicted output. Classification has several applications in a wide variety of industries. Many problems can be expressed as associations between feature and target variables, particularly when labeled data is available. Classification can be used to build applications for email filtering, speech-to-text, handwriting recognition, biometric identification, document classification, and much more. Churn prediction is when you use machine learning classification to predict whether a customer will discontinue a service. Customer segmentation is when you use classification to predict the category to which a customer belongs. You can also use classification to predict whether a customer will likely respond to an advertising campaign. Let's explore additional use cases of classification. Suppose a bank is concerned that some of their loan applicants may be unable to repay their loan. The bank uses historical loan default data to predict which customers are likely to default. Here, a classifier can be trained to use customer information like age, income, and credit debt levels to learn whether they will default. Given a new customer and the same information, but without the knowledge of the likelihood of defaulting, the trained classification model predicts whether the customer is likely to default. This is an example of a binary classifier, as its predictions are limited to two possible classes. Now, consider the following example of a multi-class classifier used to help prescribe various drugs. Imagine that you collected data about a set of patients, all of whom suffered from the same illness. During their course of treatment, each patient responded positively to one of 3 medications. You can use this labeled data set with a classification algorithm to build a classification model that can predict which drug might be appropriate for a future patient with the same illness. You can use many different types of algorithms to build your classification model. Some common machine learning classification algorithms include naive Bayes, logistic regression, decision trees, k-nearest neighbors, support vector machines, and neural networks. Algorithms like logistic regression, KNN, and decision trees can learn how to distinguish multiple classes. Many classification algorithms are not able to make distinctions between more than 2 classes, but you can use them as components for multi-class classifiers. Strategies for extending binary classifiers to handle multiple classes include one versus all classification and one versus one classification. The one versus all scheme implements a set of independent binary classifiers, one for each class label in the dataset. Each classifier is assigned a single label that defines its target class. Each classifier's task is to make a binary prediction for every data point about whether it has the given label, a one versus the rest classifier. As you can see, if there are k classes, there will be exactly k binary classifiers contributing. Let's understand how the one versus all strategy decomposes a set of data points. The algorithm works on each class label, one at a time, with a trained outcome showing the points predicted to have a given color. Notice also that a given data point might not belong to any of the classes, as it might not get picked up by any of the individual classifiers. Such unclassified points fall into another class. This property might be useful for identifying outliers or noise. With the one versus one strategy, instead of each classifier deciding whether a point belongs to a class, the question changes from, is it this, to, is it this or is it that? Given a set of classes, consider all possible pairs of classes. For each pair of labels, a classifier is trained on the subset of the data corresponding to the 2 labels and decides which class each point belongs to. The process continues until all classifiers are trained. The final class label assigned to each point may be decided by a voting scheme. The simplest scheme is by popularity, meaning the class predicted by the most binary classifiers wins. Here, green is the winner. What if there is a tie? Here, we have 3 classes with the same number of votes. In a scenario where that is possible, it would be better to use an improved scheme, weighing each vote by the confidence level or probability assigned to that class for each classifier. Alternatively, you could try using one versus all classification instead. In this video, you learned that classification is a supervised ML method that uses fully trained models to predict labels on new data. Classification can be used for churn prediction, customer segmentation, and predicting advertising campaign responsiveness. Use cases of classification also include loan default prediction and multi-class drug prescription. Classification has several algorithms, which also include multi-class classifiers. Binary classifiers can be extended to handle multiple classes by using certain strategies. The one versus all scheme implements independent binary classifiers, one for each class label. The one versus one strategy answers the question, is it this or is it that? Welcome to Decision Trees for Machine Learning. After watching this video, you will be able to define decision trees, describe how to build decision trees, explain how decision trees learn. A decision tree is an algorithm that can be visualized as a flowchart for classifying data points. In a decision tree, each internal node corresponds to a test, each branch corresponds to the result of the test, and each terminal or leaf node assigns its data to a class. A decision tree can be built by considering the features of a dataset one by one. Imagine that you're a researcher compiling data for a medical study. You would already have collected data about a set of patients who suffered from the same illness. During their course of treatment, each patient responded to one of 2 medications. Let's call them drug A and drug B. Suppose you want to build a model to predict which drug might be appropriate for a future patient with the same illness. The features of this dataset are age, gender, blood pressure, and cholesterol of our group of patients, and the target is the drug that each patient responded to. You would use the training part of the dataset to build a decision tree and then use it to predict the class of an unknown patient. In essence, to produce a decision on which drug the patient is likely to respond to. The decision to prescribe drug A or B will be based on historical data for a large set of patients diagnosed with the same disease. The tree starts by assigning a diagnosed patient to their age category, which can be young, middle-aged, or senior. If the patient is middle-aged, the decision tree suggests drug B. It also suggests drug B if the patient is young and male or a senior with normal cholesterol. On the other hand, if the patient is a young female or a senior with high cholesterol, the tree's branches lead to a prescription for drug A. A decision tree is trained by growing it as follows. Start with a seed node and label training data. Train the node on its assigned data by finding the feature that best splits the data into its pre-labeled classes according to a pre-selected splitting criterion. Each such split partitions the node's input data, and each partition is passed along its branch to a new node. Repeat the process for each new node, using each feature only once. The tree grows until all nodes contain a single class each, or you run out of features to select, or a pre-selected stopping criterion is met. A decision tree stops growing when a stopping criterion is met. This is also known as preemptive tree pruning. For instance, you can set stopping criteria for your model when the following criterion is met. Maximum tree depth is reached, minimum number of data points in a node have exceeded, minimum number of samples in a leaf have exceeded, decision tree has reached the maximum number of leaf nodes. Alternatively, you can also stop a tree from growing by cutting branches that don't significantly improve system performance. There are several reasons why you might want to prune a decision tree. If the tree is too complex, you might be overfitting it to the training data. If you have too many classes and features, the tree might be capturing noise and irrelevant details. Pruning simplifies your decision tree model and makes it amendable to generalization. A pruned tree is more concise and easier to understand. Pruning also results in better predictive accuracy. Decision trees are built using recursive partitioning to classify the data. The decision tree algorithm must select a feature that best splits the data at each node to train a tree. To do this, you must select a splitting criterion to measure the split quality for determining the best split. Two common split measures are information gain, which is also called entropy reduction, and Gini impurity. Consider the 14 patients in our data set. The decision tree algorithm chooses the most predictive feature to split the data on. For example, the feature that best distinguishes the patient classes it assigns. Suppose it starts by testing cholesterol as the first feature to split on. The tree assigns patients to two nodes, high and normal. As you can see, if the patient has high cholesterol, we cannot say with high confidence that drug B might be suitable for him. Also, even if the patient's cholesterol is normal, we still don't have sufficient evidence or information to determine whether either drug A or drug B is suitable. Cholesterol might not be the best attribute to split on. We're looking for the best feature to decrease impurity of patients in the leaves, so let's try another feature. This time, we pick the sex feature of patients. The decision tree splits patients into two branches, male and female. For females, the sex split classifies most patients as drug B. For males, the distinction between drugs A and B diagnoses is less clear. Further splitting the male node using the cholesterol feature results in two pure nodes. The terminal leaves in which all patients fall into a single class or prescription. The algorithm continues branching until it reaches a stopping criterion. Entropy is the measure of information disorder, or randomness in a dataset. It measures how random the classes in a node are, or how uncertain the feature split result is. In decision trees, you look for trees that have the smallest entropy in their nodes. You can calculate the entropy of a node using the entropy formula, where PA and PB are, respectively, the proportions of drug A and drug B patients in the node. If the classes are completely homogeneous, the entropy is 0, and if they are equally divided, the entropy is 1. For example, if PA equals PB equals 1/2, then the formula yields 1/2 times -1 minus 1/2 times -1 equals 1. You don't need to calculate these, of course, as it's calculated by the libraries or packages that you use. Information gain is the entropy of a tree before the split minus the weighted entropy after the split by a feature. For example, using cholesterol as the feature to split on for all patients yields an information gain of 0.042. You can consider information gain and entropy as opposites. As entropy decreases, the information gain, or amount of certainty, increases. Constructing a decision tree is all about finding features that return the highest information gain. Decision trees are advantageous because they can be visualized. This means you can see exactly how it makes decisions, which makes them highly interpretable. Since the tree grows by gradually selecting the next best feature to split on, you can gain insights about how important or predictive each feature is. A decision tree is an algorithm for classifying data points. Decision trees are built by considering the features of a dataset one by one. In a decision tree, each internal node corresponds to a test. Each branch corresponds to the result of the test. And each terminal, or leaf node, assigns its data to a class. In this video, you learned how to train a decision tree, how to prune a decision tree, and how to select the features that best splits the data at each node when you're training a tree. You also learned about the information gain and Gini impurity split measures. Decision trees help in visualizing a data model and predicting outcomes based on the information in a dataset. Welcome to Regression Trees. After watching this video, you will be able to describe a regression tree and recognize how it is different from classification. You will also be able to explain how to create a regression tree. A regression tree is analogous to a decision tree that predicts continuous values rather than discrete classes. The distinguishing feature between classification and regression is the characteristic of the target or labeled data. In classification, the target variable is categorical, such as true or false. In regression, the target is a continuous value, such as temperature or salary. When a decision tree is adapted to solve regression problems, it is called a regression tree. Let's compare classification trees with regression trees to understand how they're different. The target of a classification tree is to classify data into discrete sets, whereas a regression tree aims at predicting continuous target variables. Hence, the target variable for a classification tree is categorical but floating for a regression tree. The prediction at leaf nodes for a classification tree is a class label majority vote, whereas for a regression tree, it is the average value of target values. Some use cases of classification trees are spam detection, image classification, medical diagnosis. Regression trees are used for predicting revenue, temperatures, and wildfire risk. Regression trees are created by recursively splitting the dataset into subsets to maximize information gain from data splitting. This process generates a tree-like structure and minimizes the randomness of the classes assigned to the split nodes. Let's consider this example. Given a continuous feature from a dataset and a trial threshold value, alpha, the data in a node is split into two subsets according to whether the data is greater than or less than alpha, and the corresponding points are assigned to the left and right nodes. If the feature is binary, consisting of two classes, then the split is according to the two classes. You make a prediction at each node based either on a class voting scheme, as with decision trees, or by using the average of the target values in the node. The predicted value, y hat, for a given node is defined as the average of the actual target values, y, I of the data points in the node. You could use other statistics, like the median value, to assign the prediction. This would be preferable when your data is skewed. For normally distributed data, the median is comparable to the mean, but the median is more expensive to compute. Instead of using the entropy or information gain criteria to measure the quality of a split, as for decision trees, regression trees select features that minimize the error between the actual values, y I in the resulting nodes, and the predicted value, y hat. A natural criterion for measuring the split quality of a given feature uses the mean squared error, or MSE. Notice that this amounts to measuring the variance of the target values within each node, which gauges how spread out the values are. The smaller the variance is, the more closely the values agree. To measure the quality of a split, the weighted average of the MSEs of each split node can be used. The weighted average is calculated as average MSE equals 1 over the number of observations in the two split nodes times the sum of the number of observations in the left split times the MSE of the left split, and the number of observations in the right split times the MSE of the right split. The lower this value, the lower the variance, and thus the higher the quality of the split. During training, the tree finds the feature and threshold that best splits each node. For each potential split of a feature, the tree calculates the MSE for the left and right subsets. The MSE of the split is a weighted average of the MSEs of the subsets. The split with the lowest weighted MSE is chosen. This process minimizes the variance in the predicted values and improves the accuracy of the regression tree. For a binary feature, instead of using thresholds, the data is simply separated into its two classes, and the split quality is just the weighted average of the class MSEs. The weighted MSE has only one possible result, so it is already optimized. For a multi-class feature, you can use a strategy like 1 versus 1 or 1 versus all to generate a set of possible binary splits. Then, for each binary split, calculate the weighted average of the MSEs. Select the split that minimizes the weighted MSE and thus the lowest prediction variance. How can you choose a set of trial thresholds to split a continuous feature on? There are many ways. Here's one strategy. Start by sorting the feature's values so that xi is less than or equal to xj for all indexes I less than j. Drop any duplicated values so that xi is strictly less than xj for all I less than j. Define your candidate thresholds, alpha I as the midpoints between each pair of consecutive values. Alpha I is half of xi plus xi plus 1. Choose the threshold that minimizes the weighted MSE for its data split. This is an exhaustive search method that doesn't scale well to big data. For very large data sets, selecting a sparse subset of these thresholds can improve efficiency at the cost of accuracy. The method also assumes the target values, x, are uniformly distributed. For efficiency, you should consider the distribution when sampling the thresholds. In this video, you learned that a regression tree is analogous to a decision tree that predicts continuous values. In classification, the target variable is categorical, and in regression, the target is a continuous value. Regression trees are created by recursively splitting the dataset into subsets to maximize information gained from data splitting. MSE is a natural criterion for measuring the split quality of a given feature. The regression tree finds the feature and threshold that best splits each node during training. The feature can be binary or multi-class. Finally, you learned that you can choose continuous feature trial thresholds in multiple ways depending on data size. Welcome to Supervised Learning with SVMs. Support vector machines, or SVMs, are used for classification. After watching this video, you will be able to describe SVM, identify Python tools for SVM, and discuss SVM applications. Support vector machines, or SVM, is a supervised learning technique for building classification and regression models. It maps each data instance as a point in multidimensional space where the input features are represented as a value for a specific coordinate. SVM classifies input data by identifying the hyperplane, which distinctly differentiates two classes. Thus, these points are fundamental to the dataset. In a classification task comprising two features, the hyperplane is a linear line that segregates and classifies the dataset. Every time new inputs are added to the task, their classification depends on which side of the hyperplane they land. The primary goal of SVM is to create a hyperplane that segregates a dataset into two parts and finds the largest margin. In this example, the dataset comprises a collection of two classes, red triangle and blue square. The larger the margin, the better the model's accuracy on new, unseen data. Data is often noisy and overlapping in real-world scenarios, making perfect separation impossible. SVM can incorporate a soft margin, which allows it to tolerate misclassifications while maximizing the margin. The balance between maximizing the margin and minimizing the number of misclassifications is controlled by a parameter, c. A smaller c allows more misclassifications, softer margin, while a larger c forces a stricter separation, harder margin. Rudimentary SVMs are binary classification machine learning algorithms. Binary SVMs assume that two classes are linearly separable. However, SVMs can also be adapted to solve regression problems. SVMs try to divide data into two classes by finding a decision boundary. For example, this chart shows two classes as red and blue data points based on two features. The decision boundary is a hyperplane that maximizes the margin. In a two-dimensional feature space, the decision boundary is a line. The margin is the distance from the hyperplane to the closest points from each class. These nearest point representatives from each class are support vectors. Without getting into the details of the mathematics involved in the derivation of the optimization problem, consider this 2D example. Using the training data and assuming the data has been normalized, the objective is to find a weight vector and a value b, called the bias term, such that a, the inner product of w with itself is minimized, which amounts to minimizing the length of w, and b, for every observation, or data point x, and target value y, the product of y and w transported x plus b is greater than or equal to 1. Therefore, the algorithm's output is the line's values, w and b. You can make classifications using this estimated line. Adding input values into the line equation lets you calculate whether an unknown point is above or below the line. If the equation returns a value greater than 0, the point belongs to the first class, which is above the line, and vice versa. Consider a 2D object of a non-linearly separable pair of classes. As you can see from the 2D chart, there are two non-overlapping classes with concentrically circular shapes. You can imagine these points as analogous to map contours, representing their heights. Clearly, these classes are not linearly separable. Let's transform the features of the 2D object so that it takes on a parabolic shape. Let's create a new 3D object by adding the new feature as the z-axis. It's a bit difficult to interpret 3D objects, but as you can imagine, the two classes are now clearly separated by a horizontal plane. You can use this plane to classify new cases according to whether they lie above or below the plane. Mapping data into a higher dimensional space like this is called kerneling, where the kernel is a quadratic polynomial in this case. With real-world data, there is no straightforward way to know which kernel function performs best. Scikit-learn provides you with a choice of kernel functions to use with SVM. A linear kernel is the default and corresponds to the usual SVM model. Parabolic embedding is implemented by choosing the polynomial option. Radial basis functions, or RBFs, which score high for points close to each other and an exponentially decreasing score as points become more distant. The sigmoid is the same function used for logistic regression. To see how support vector machines work for regression, consider this chart. It'll help you build some intuition without going into mathematics. The synthetic data depicted by the orange data points represents a noisy, nonlinear, continuous target variable as a function of an input feature. The blue curve displays the support vector regression, or SVR model prediction using a radial basis function, or RBF kernel. The shaded light blue region represents the epsilon tube around the prediction. Points falling within the epsilon tube are shaded yellow. Epsilon is a parameter of the SVR learning algorithm that you can select to define a margin around the prediction curve. Points falling outside the margin are interpreted as noise, and points inside as signal. In the first case, epsilon is 0.2, and in the second, epsilon is 0.4. SVM has many advantages. For example, it's effective in high-dimensional spaces, it's robust to overfitting, it excels on linear separable data, and it works with weakly separable data using weak margin option. SVM also has some limitations. For example, it's slow for training on large data sets. It's sensitive to noise and overlapping classes, and it's sensitive to the choice of kernel and regularization parameters, which are non-trivial to determine. When should you use SVM? SVM is good for image analysis tasks, such as image classification and handwritten digit recognition. It's also highly effective for parsing, spam detection, and sentiment analysis. SVM can be used for machine learning problems, such as speech recognition, anomaly detection, and noise filtering. In this video, you learn that support vector machines, or SVM, is a supervised learning technique for building classification and regression models. SVMs try to divide data into two classes by finding a decision boundary, which is a hyperplane that maximizes the margin. Scikit-learn provides many kernel functions, such as linear, polynomial, RBF, and sigmoid for using with SVM. SVM has many advantages. It's effective in high-dimensional spaces and robust to overfitting. However, it also has some limitations. It's slow for training on large data sets and sensitive to noise and overlapping classes. You should use SVM for image recognition, spam detection, and machine learning problems. Welcome to Supervised Learning with KNN. After watching this video, you'll be able to explain what k-nearest neighbors, or KNN, is, describe how a KNN algorithm works, and discuss how k affects the outcome of the KNN algorithm. K-nearest neighbors, or KNN, is a supervised machine learning algorithm that takes a group of labeled data points and then uses them to learn to label other data points. KNN is used for both classification and regression. In KNN, data points near each other are said to be neighbors based on the paradigm. Points close to each other should have similar features, and therefore tend to be like each other. Let's consider this chart. Here, for each queried data point, KNN finds its nearest data points and makes a prediction based on the known target labels of the query point's neighbors. You also need to define mathematically what is meant by a neighbor. Let's understand how KNN works. In a classification problem, KNN works as follows. First, pick a value for k. Then, calculate the distance from each unlabeled query point to all labeled cases in the training data. Search for the k observations in the training data that are nearest to the query point. Predict the value of the given data point using the most popular class value from the k nearest neighbors. In the case of regression, you would predict using the average or median of target values. Let's see how you can calculate the similarity between two data points in classification. Let's consider this data set comprising 50 samples, each from the 3 species of iris: Iris setosa, Iris virginica, and Iris versicolor. Each row in the data set contains 4 features listed in centimeters: sepal length, sepal width, petal length, and petal width. We want to use this data set to train KNN to classify the 4 iris types. Here is a scatter plot of the iris flower data between 2 features, sepal length and petal length. The points are the sepal petal length pairs labeled with their actual iris type, setosa, versicolor, or virginica. Now consider the region bound by the box and the point at the center of the red circle. Its 3 nearest neighbors are indicated by the line segments connecting to them. Using a majority vote, KNN would correctly classify this point as blue, or virginica. Looking at another point, showing its nearest 3 neighbors, you can see that the majority class is green, or versicolor. Thus, KNN would incorrectly classify this iris. Illustrated here is the decision boundary for the KNN classification result using k equals 3 nearest neighbors and 2 input features, sepal length and petal length. The model was generated with the k neighbors classifier from Scikit-learn. The 3 different colored regions indicate which of the 3 classes or types of irises KNN predicted for each pair of sepal and petal lengths. The points are the sepal petal length pairs labeled with their actual iris type, setosa, versicolor, or virginica. As you can see, KNN correctly classified most of the irises with an accuracy of 93%. To find an optimal value for k, you can test a range of values using a labeled test dataset and measure accuracy. Once you've done so, choose k equals 1, use the training part for modeling, and calculate the prediction accuracy using all samples in your test set. Repeat this process, increasing the k, and see which k is best for your model. For example, k equals 4 will give you the best accuracy in this case. The KNN algorithm is a lazy learner, so it doesn't learn in the sense that other machine learning models do. It stores the training data and makes predictions for each query point based on its distances to all points in the training data. Thus, it is still a supervised model because it must calculate all distances from each query point to the training points, then sort the observations by increasing distance, and finally, select the top k observations. Now, how does k affect the outcome of the KNN algorithm? If k is small, the values assigned to unlabeled observations will tend to fluctuate, causing overfitting. If k is large, then KN will smooth out the finer details and cause underfitting. Somewhere in between, there will be a happy medium value for k. In classification, the majority voting algorithm becomes unreliable when the class distribution is skewed. More frequent classes tend to dominate the prediction of the new example because they are more prevalent among the nearest neighbors owing to their higher number. To overcome this challenge, you can weigh the classification by considering the distance from the test point to each of its KNN. When features have large values, they will dominate the distance measure and the predictions. Artificially more important features can cause biased or low accuracy predictions. Features need to be scaled to remove this effect, and the simplest way is standardization. Including an irrelevant feature is like adding noise. Noisy data requires a higher value of k to avoid overfitting, which in turn drives up computational cost and diminishes accuracy. Keeping only relevant features lowers the optimal k and improves both accuracy and computational efficiency. Features must be relevant to the problem. Redundant features add computational cost with no expected improvement in accuracy. Being able to identify relevant features comes from domain knowledge. To check whether an independent feature is important, you can tune k with and without the feature and evaluate the change in model performance. In this video, you learned that KNN is a supervised machine learning algorithm that uses labeled points to learn how to label other points. KNN is used for classification and regression. To find an optimal value for k, you can test a range of values using a labeled test data set and measure accuracy. When the class distribution is skewed, there's a disadvantage in the basic majority voting classification. A possible resolution can be to weigh the classification or by abstraction in data representation. Selecting only relevant features lowers the optimal K and improves both accuracy and computational efficiency. To check whether an independent feature is important, you can tune K with and without the feature and evaluate the change in model performance. Welcome to Bias, Variance, and Ensemble models. After watching this video, you'll be able to analyze the impact of bias and variance on accuracy and precision. You'll also be able to explain the bias-variance trade-off in model complexity, evaluate techniques to mitigate bias and variance, and analyze the outcomes of bagging and boosting methods. Let's understand bias and variance with the 4 dart boards shown in the image. Closely grouping the darts near the center of the board indicates high accuracy and low bias. The top 2 boards demonstrate low bias, meaning they are more accurate, while the bottom 2 show higher bias, making them less accurate. Think of bias as how on-target or off-target the darts are. Variance measures how spread out the darts are, representing precision. The dartboards on the right display higher variance, meaning the darts are more spread out, while the boards on the left show lower variance, with the darts grouped closer together. As shown on the top left board, achieving a high score requires both low bias for accuracy and low variance for precision. Prediction bias refers to how precise a model's predictions are. It's measured by the average difference between what the model predicts and the actual target values in the data. A perfect predictor has zero bias. This chart illustrates prediction bias. The blue line represents the linear ordinary least squares fit for the blue data points. It has a bias of 0.22. The red line depicts the same model shifted down by 4 units. It has a much higher bias of 4.22. Prediction variance measures how much a model's predictions fluctuate when trained on different subsets of the same dataset. When a model exhibits high prediction variance, it becomes extremely sensitive to changes in the selected training data. High variance causes the model to overfit the training data and track noise or outliers present in the training data. In contrast, models that generalize well to unseen data are necessarily less sensitive to noise. They have low prediction variance. This chart displays orange data points that follow a nonlinear pattern. Each model is fitted using a randomly sampled training dataset. The curves would align almost perfectly if the prediction variance were near zero. However, you can observe differences between the curves, especially at the beginning and end of the data. This variation indicates some prediction variance, reflecting instability in the model's predictions. This plot illustrates how bias and variance change as your model becomes more complex and better at predicting the data it's trained on. As model complexity increases, bias, represented by the blue curve, tends to decline, while variance, shown by the green curve, rises. When model complexity is low, bias is high, leading to poor predictions even on training data. This is known as underfitting. Conversely, high model complexity results in high variance, meaning the model becomes overly sensitive to the training data and performs poorly on unseen data, resulting in overfitting. However, there's a crossover point marked by the vertical dashed line where the model's complexity is just right. As the plot indicates, there will always be some generalization error that cannot be eliminated, such as random noise in the data. A weak learner is a supervised machine learning model that performs only slightly better than random guessing. These models are characterized by high bias and low variance, which often leads to underfitting. In contrast, strong learners exhibit low bias and high variance, resulting in a tendency to overfit the data. Bagging and boosting are well-known ensemble methods that effectively balance bias and variance. Decision or regression trees are commonly chosen as base learners in ensemble learning because their bias and variance can be easily adjusted by altering their depth. The model predictions shown here utilize the same modeling algorithm, repeatedly trained on bootstrapped subsets of data. You can observe the variance at both ends of the family of curves. Now, imagine if you were to perform this process multiple times and then average the predictions. This technique is known as bagging or bootstrap aggregating. As illustrated by the dashed curve, averaging the models across numerous iterations significantly reduces prediction variance while also lowering the risk of overfitting. Random forest is a bagging method that trains multiple decision trees on bootstrap datasets. These trees don't need to be very deep. Instead, the focus should be on minimizing prediction bias. Shallow trees have high prediction variance, and aggregation significantly reduces this variance while only slightly increasing bias. Boosting is an ensemble modeling technique that builds a series of weak learners, each aimed at correcting the errors of the previous one. By systematically reducing prediction error, boosting helps lower prediction bias. The final model is formed as a weighted sum of these weak learners. In each iteration of the process, the weights of misclassified data from the previous model are increased, while the weights of correctly classified data are decreased. This reweighting helps the algorithm focus on correcting the mistakes. The model's weights are updated based on the performance of each weak learner. Popular boosting algorithms include gradient boosting, XGBoost, and AdaBoost. This graph demonstrates how bagging and boosting can help mitigate the bias-variance trade-off by strategically adjusting model complexity. Boosting increases model complexity and decreases bias. In contrast, bagging increases variance. This table illustrates how ensemble methods can be used to address common issues in machine learning. Bagging aims to mitigate overfitting by combining multiple base learnings that are high variance and low bias. These base learners are trained in parallel on bootstrap data samples. Bagging helps reduce variance. Boosting aims to mitigate underfitting by sequentially training base learners that are low variance and high bias. Each subsequent base learner builds on the previous result, gradually reducing bias. In this video, you'll learn to analyze bias and variance and how they impact accuracy and precision. Explain prediction bias and how it measures the accuracy of predictions. Analyze prediction variance to measure how much a model's predictions fluctuate. Explain the bias-variance trade-off and how bias and variance change as your model becomes more complex. Explain mitigating bias and variance and the concept of weak and strong learners. Analyze bagging or bootstrap aggregating to observe variance at both ends of a family of curves. Explain random forests to train multiple decision trees on bootstrap data sets. And finally, analyze bagging and boosting outcomes to manage bias and variance. Welcome to this video on clustering strategies in real-world applications. After watching this video, you will be able to explain the concept of clustering and its various applications. You will learn how to apply k-means clustering to segment customers based on their characteristics. Additionally, you will gain an understanding of the different types of clustering methods, including partition-based, density-based, and hierarchical clustering. Finally, you will be equipped to analyze agglomerative and divisive hierarchical clustering, exploring their distinct approaches to grouping data points. Clustering is a machine learning technique that automatically groups data points into clusters based on similarities. Clustering can be applied in various scenarios, such as identifying music genres, segmenting user groups, or analyzing market segments. This method can use just one feature or multiple features in data to form meaningful clusters. This dataset includes historical customer features and loan default status. Classification algorithms, being supervised, learn to predict categorical labels from labeled data. Here, based on the labeled historical data, a decision tree model is trained to predict if a new customer will default on a loan. Clustering is like classification but works with unlabeled data, independently finding patterns to form clusters. Here, a k-means clustering model segments customers with similar characteristics into 3 clusters, indicated by the blue, light blue, and red rows. The model operates without knowing if a customer has defaulted, as that data is unavailable and not part of its design. In exploratory data analysis, clustering uncovers natural groupings, such as customer segmentation for targeted marketing. Clustering boosts pattern recognition by grouping similar objects and aiding in image segmentation, such as detecting medical abnormalities. Clustering helps anomaly detection by identifying outliers and detecting fraud or equipment malfunctions. In future engineering, clustering creates new features or reduces dimensionality, improving model performance and interpretability. In data summarization, clustering simplifies data by summarizing it into a small number of representative clusters. Clustering reduces data size by replacing data points with cluster centers, which is useful for image compression. Finally, clustering identifies essential features that distinguish clusters. Partition-based clustering algorithms divide data into non-overlapping groups. The most common method, k-means, identifies k-clusters with minimal variance. These algorithms are efficient and scale well with large data sets. Density-based clustering algorithms create clusters of any shape, making them suitable for irregular clusters and noisy data sets. An example is DBSCAN algorithm. Hierarchical clustering algorithms organize data into a tree of nested clusters, each containing smaller subclusters. This process generates a dendrogram, revealing relationships between clusters. The two main algorithms are agglomerative, which merges clusters, and divisive, which splits them. These algorithms are intuitive and effective for small to mid-sized data sets. This partition-based clustering result uses the make-blobs function from Scikit-learn, generating 3 color-coded clusters in the scatter plot. Here are 2 clustering results using the make-moons function from Scikit-learn that generates interlocking half circles. Both use color to distinguish clusters visually. On the left, the partition-based clustering struggles to separate the shapes, partitionating the data along a red curve. In contrast, the density-based clustering successfully separates the shapes but creates an unnecessary third cluster of 3 points. This chart, created by UCLA biologists, presents genetic data from over 900 dogs across 85 breeds and 200 wild gray wolves globally. They analyzed 48,000 genetic markers using molecular techniques. The diagram illustrates hierarchical clustering, grouping animals based on genetic similarities in a tree-like structure where each node represents a cluster of child clusters. There are 2 main strategies for constructing hierarchical clustering trees: divisive and agglomerative. Divisive clustering uses a top-down approach. It starts with all observations in a single root cluster, which is iteratively split into smaller child clusters. Agglomerative clustering employs a bottom-up approach. Each observation begins as an individual cluster, and similar clusters are merged into larger parent clusters. Let's explore the agglomerative hierarchical clustering algorithm, which uses a bottom-up approach. First, select a metric to measure the distance between clusters, such as the distance between their centroids. The process begins by initializing n clusters, with each cluster containing a single data point. Next, a distance matrix is computed, which is an n×n matrix that displays the distances dij between each pair of points I and j. Repeat the following steps until you achieve the desired number of clusters or merge all points into one cluster. Merge the 2 closest clusters based on the selected distance metric. Update the proximity metric with the new distance values. Let's examine the divisive hierarchical clustering algorithm, which takes a top-down approach. Start with the entire data set as one cluster. Partition this cluster into smaller clusters based on similarities or dissimilarities. Continue splitting each cluster into 2 until a stopping criterion, which is a minimum cluster size, is reached. Imagine you want to group 6 cities in Canada based on their distances from one another. The distance matrix represents the distances between each pair of cities. The algorithm starts with 6 clusters, each representing a city with the first 2 letters of its name. The initial task is identifying which 2 clusters to merge based on a distance measure, like flight distance. Reviewing the distance matrix shows that Montreal and Ottawa are the closest clusters, so they combine into the next parent cluster. As the algorithm progresses, you can visualize the hierarchy of clusters with a dendrogram, as indicated by the red oval. The distance matrix combines the rows and columns for Montreal and Ottawa in the Ottawa-Montreal cluster. The distances to this new cluster are updated and calculated as the midpoint between the 2 cities. Next, look for the closest clusters again. The Ottawa-Montreal and Toronto clusters are the nearest, forming the Toronto-Ottawa-Montreal cluster. As the algorithm progresses, a dendrogram visualizes the hierarchy of clusters, as shown by the red oval. Next, the updated distance matrix shows that Vancouver and Edmonton are the closest. Similarly, the agglomerative algorithm merges clusters into one, completing the dendrogram. In this video, you learned to explain the concept of clustering and its applications, apply k-means clustering to segment customers based on characteristics, explain density-based clustering and how they are suitable for irregular clusters, explain hierarchical clustering and how it generates a dendrogram, explain strategies for hierarchical clustering, divisive and agglomerative, analyze agglomerative hierarchical clustering and its bottom-up approach, analyze divisive hierarchical clustering and its top-up approach. Welcome to k-means clustering. After watching this video, you will be able to describe k-means clustering and explain how the k-means algorithm works. You will also be able to discuss how to determine k. K-means is an iterative, centroid-based clustering algorithm that partitions a dataset into similar groups based on the distance between their centroids. K-means divides data into k non-overlapping clusters where k is a chosen parameter. The k clusters are constructed to have minimal variances around their centroids and maximum dissimilarity between clusters. Let's understand this definition with the help of this chart showing a cluster of data points. At the center of the cluster is the centroid marked with a red X. This is the average position of all points in the cluster. Data points nearest to a centroid are grouped within the same category. A higher K value, or the number of clusters, signifies smaller clusters with greater detail, while a lower K value results in larger clusters with less detail. Let's look at how to use K-means. First, initialize the algorithm. Choose the number of clusters that you would like to partition the feature space into, and randomly select K starting centroid locations. These initial centroids can be data points or other points from the feature space. Next, assign centroids. Iteratively assign points to clusters and update their centroids. First, compute the distance matrix consisting of the distances from each point to each centroid. Then, assign each data point to the cluster with the nearest centroid. Update each cluster centroid as the mean of the cluster's data points. Repeat until the centroid positions stabilize or you reach maximum iterations. The algorithm converges once the centroids stop moving. Here's an experiment demonstrating how K-means updates centroids and cluster points with each iteration. The demo starts with two unknown classes comprising circular clusters of points in red and blue and two randomly selected initial centroids in gold, each represented by an X and the plus symbol. With each iteration, you can see the centroids getting closer to their final destinations. Iterations 3 and 4 are identical. Thus, K-means have already converged by iteration 3. Although the final clustering contains a few mislabeled points, K-means does a good job of separating them. However, K-means doesn't perform very well on imbalanced clusters. In this experiment, the unknown classes, indicated by the pair of circular clusters of points in red and blue, differ in their number of points. The red cluster has 200 points, and the blue one has 10. Interestingly, the results in the first iteration is quite good. The centroid updates for the larger cluster stabilize very quickly. However, the smaller cluster's centroid drifts closer to the larger cluster's centroid, and its cluster consumes more and more of the larger cluster's points. K-means assumes that clusters are convex, meaning that any line drawn between 2 points remains within the cluster. The figure here shows a non-convex set of points colored blue. The boundary defined by the blue line segments approximates the boundary of the set of points. The red lines outline what is called the convex hull of the points. The algorithm also assumes that the clusters contain approximately the same number of points. Because statistical variance is sensitive to outliers, K-means can perform poorly in the presence of noise. As a partition-based algorithm, K-means is efficient and scales well to big data. The goal of K-means is to minimize the within-cluster variance for all clusters simultaneously. Mathematically, this means a double sum over each cluster, I, and each point, x, within each cluster, Ci of the squared distance between x and its cluster centroid, mu I. Here are the results from 3 experiments to illustrate how well K-means performs under different conditions. The 3 scatter plots on the left are from data generated with Scikit-learn's make-blob function. The 3 blobs represent 3 different clusters. The difference between the 3 datasets is the standard deviation of each blob, increasing from 1 to 4 to 15. Higher values disperse the blobs and they become visually less distinguishable. On the right are each experiment's K-means clustering results for k equals 3. The red X's indicate the K-means cluster centroids. K-means does not know the classes or colors assigned to the blobs in the input data. The goal of these experiments is for K-means to uncover these 3 classes. As you can see, K-means has distinguished the blobs quite well for standard deviations of 1 and 4. Where the blobs overlap, the resulting clusters have errors. It would be unreasonable to expect any clustering algorithm to untangle blobs where the standard deviation is 15. However, K-means did what was instructed to do and generated 3 clusters anyway. Intuitively, you might expect at most 2 clusters to be found, the core and outlying points. If the input data had 3 class labels as depicted, the 2 features would be incapable of separating them. More features would be needed to accomplish this separation. Observe that, as the standard deviation of the blobs increases, the cluster centroids that K-means finds get closer together. What if K differs from the unknown number of classes in the input data? Here, the experiment is run with K equals 2 clusters for K-means to determine, and 3 blobs with 3 unknown classes are given. For a standard deviation of 1, K-means correctly identifies 1 blob and merges the other 2 into 1 cluster, with its centroid between the 2 blobs. Similarly, for a standard deviation of 4, K-means identifies 1 blob and merges most of the other 2 blobs into 1 cluster, with its centroid between the 2 blobs. When the standard deviation is 15, k-means is left with no option and must impose the two clusters onto what looks like indistinguishable data. As the standard deviation of the blobs increases, the cluster centroids that k-means finds get closer together. The two blobs gradually merge into one, and a blob can have only one centroid. When k is too large, k-means returns unacceptable results. How do you find the best value for k when you don't know much about your data? Choosing k is difficult for complex data. When the data is separable, choosing the suitable k is feasible. How do you know whether the data is separable? While obvious in 2 or 3 dimensions, you can't visualize the patterns easily for higher dimensional feature spaces. You can gain some insight by considering scatter plots between pairs of your variables to see whether any of these demonstrate separability. Some heuristic techniques for gauging k-means performance for a given k include silhouette analysis, which measures how similar a data point is to its cluster, known as cohesion, compared to other clusters, known as separation. The elbow method is a plot of the k-means objective function for different numbers of clusters, and the Davies-Bouldin index measures each cluster's average similarity ratio, with the cluster most similar. In this video, you learned that k-means is an iterative centroid-based clustering algorithm that partitions a dataset into similar groups based on the distance between their centroids. The k-means clustering algorithm categorizes data points into clusters using a mathematical distance measure from the cluster center. K-means doesn't perform very well on imbalanced clusters and assumes that clusters are convex. The objective of k-means is to minimize the within-cluster variance for all clusters simultaneously. Some heuristic techniques for gauging k-means performance for a given k include silhouette analysis, the elbow method, and the Davies-Bouldin index. Welcome to DBSCAN and HDBSCAN clustering. After watching this video, you will be able to describe DBSCAN, or density-based spatial clustering of applications with noise clustering, and explain how it works. You will also be able to describe HDBSCAN, or hierarchical density-based spatial clustering of applications with noise cluttering, and explain how it works. DBSCAN is a density-based spatial clustering algorithm that creates clusters with a density value provided by the user. The density value is positioned around a spatial centroid. The area immediately around the centroid is referred to as a neighborhood, and DBSCAN attempts to define neighborhoods of clusters with a specified density. DBSCAN can discover clusters of any shape, size, or density in your data. It can also distinguish between data points that are part of a cluster and those that should be labeled as noise. Density-based clustering is especially useful when working with datasets with noise or outliers, or when the number of clusters in the dataset is unknown. Centroid-based clustering algorithms, such as k-means and hierarchical clustering, produce spherical or convex shapes and can work well for datasets that exhibit such patterns. Centroid-based clustering assigns every point to a cluster, even when it doesn't properly fit into one, like the black outlier assigned to the blue cluster. Unfortunately, real-world data is rarely that simple. Natural patterns can have arbitrary shapes, shapes within shapes, and noise. Density-based clustering addresses these complexities by identifying connected regions of relatively high density. Let's look at how the DBSCAN algorithm works. Given a dataset of points, you first select 2 parameters, a desired minimum number of points, n, you want in a neighborhood, and the radius, epsilon, of each neighborhood. Next, working through every point in the dataset, you label it as one of the following types: a core point, which is a focal point within a cluster, if it has at least n points, including itself, within its neighborhood or radius epsilon. A border point, if the point falls within the neighborhood of a core point but doesn't have enough neighbors to be a core point, or a noise point, if it is isolated from all core point neighborhoods. Clusters are grown from core points by including their neighbors. Although border points are assigned to the same cluster as their associated core points, they are not as densely connected. Here, you can see a simulation of how DBSCAN labels points. The data consists of 2 noisy sets of points created with the half-moons function from Scikit-learn. Consider the following. Core points are labeled in blue, and each has at least n equals 4 neighbors with its epsilon radius. Border points, labeled in orange, are points that belong to the neighborhood of their nearest core point, but don't have enough nearby points to qualify as core points. Border points exist in the outer reaches of the core neighborhoods. DBSCAN is not iterative. It grows clusters in one pass without updating them once they are labeled. Any unassigned points remaining are regarded as noise. Illustrated here is a simulation of the steps DBSCAN uses to cluster points. The data consists of two noisy sets of points created with the half-moons function from Scikit-learn. The sequence of plots shows how the clusters expand and how noise points are left unlabeled at each step. At first, all points are labeled in black and treated as outliers or noise. In step 2, the algorithm identifies most of one of the half-moons as the blue points, treating the remaining points as possible noise. In step 3, DBSCAN labels most of the other half-moon as the orange points, with a few black points left over as potential noise. Finally, DBSCAN finds a third cluster in green, which is quite isolated from it, as you can see from the enveloping neighborhood. DBSCAN has done a good job of clustering the data and identifying the outlying noisy points. HDBSCAN is a variant of DBSCAN that doesn't require any parameters to be set, making it even more flexible than the original. HDBSCAN is also less sensitive to noise and outliers. It uses cluster stability, which refers to a cluster's ability to not change much when the neighboring size is adjusted within a reasonable range of radii. HDBSCAN measures cluster stability to find locally optimal neighborhood radii. This results in more robust and meaningful clusters. The technical implementation details of HDBSCAN are somewhat complex. It is a combination of agglomerative and density-based clustering. HDBSCAN starts by identifying each point as its own cluster, effectively noise, then progressively agglomerates clusters into a hierarchy by incrementally lowering the density threshold. In this way, a hierarchical tree is constructed, which gets simplified into a condensed tree where only the most stable clusters across different density levels are kept. Illustrated here is the result of running DBSCAN on a portion of the dataset from Statistics Canada that contains the latitudes and longitudes of Canadian museums. The DBSCAN parameters chosen were minimum samples in a neighborhood, equals 3, with a neighborhood radius of 0.15 scaled units. DBSCAN found around 10 clusters that seem appropriate to the human eye. However, the population density is much higher within the red ellipse, and most of the region has been lumped into a single cluster. HDBSCAN has an advantage over DBSCAN in that it adaptively adjusts the neighborhood size to reflect changes in the local densities of the points. Here, HDBSCAN was run with a minimum number of samples, equals 10, and a minimum cluster size of 3 points. Notice how the HDBSCAN result identified more distinct clusters than DBSCAN. Interestingly, in addition to finding larger connected regions of varying density, HDBSCAN tracked and distinguished connected sets of points that lie on curves. The result looks more coherent and less noisy. Of note is the level of detail provided in the relatively dense region in the east. DBSCAN didn't provide the adaptive detail that HDBSCAN did here. By tuning the parameters, you can strike a balance between mitigating outliers, capturing the level of detail, and controlling the overall number of clusters found. In this video, you learned that DBSCAN is a density-based spatial clustering algorithm that creates clusters with a density value provided by the user. Density-based clustering works well with natural patterns by identifying regions of relatively high density. DBSCAN is not iterative. HDBSCAN is a variant of DBSCAN that doesn't require any parameters to be set and uses cluster stability. Cluster stability is defined as the persistence of a cluster over a range of distant thresholds. Welcome to this video on clustering, dimension reduction, and feature engineering. After watching this video, you will be able to explain clustering, dimension reduction, and feature engineering and how these techniques work together to enhance model performance. You will also learn about dimension reduction and its role in simplifying data structures and improving outcomes. Additionally, you'll analyze the application of dimension reduction in face recognition and explore how clustering can facilitate feature selection. Clustering, dimension reduction, and feature engineering are complementary techniques in machine learning and data science. They work well together to improve model performance, quality, and interpretability. Clustering helps with feature selection and creation while supporting dimension reduction to enhance computational efficiency and scalability. Dimension reduction simplifies the visualization of high-dimensional clustering, aiding feature engineering and improving model quality. It also reduces the number of features required for a data model. Dimension reduction is commonly used as a pre-processing step for clustering, simplifying data structure and improving outcomes. High-dimensional data poses challenges for distance-based clustering algorithms like k-means and DBSCAN. As dimensionality increases, volume expands rapidly, causing data points to become sparse and less similar. This leads to smaller clusters requiring more data to fill gaps. Techniques like PCA, T-SNE, and UMAP are employed to reduce dimensions before applying clustering algorithms, enhancing efficiency. This example uses eigen faces as input features for supervised face recognition. PCA is performed on an unlabeled face dataset, extracting the top 150 eigenfaces from a total of 966 faces. These 150 eigenfaces form an orthonormal basis for the feature space defined by the face dataset. The input data is then projected onto this eigenface basis, and an SMV is trained to predict faces. Dimensionality reduction techniques preserve the key features for identifying faces while minimizing computational load. The facial recognition task accurately predicts 12 faces, as illustrated in this image. This chart illustrates the quantitative evaluation of the model's quality on the dataset. Clustering results cannot be visualized directly when working with feature spaces beyond 3 dimensions. However, advanced dimension reduction techniques can project these clustering outcomes into 2 or 3 dimensions, significantly improving visual interpretation. Methods such as PCA, T-SNE, and UMAP allow for meaningful projections of higher dimensional clusters into 2 or 3 dimensions. This enables the creation of scatter plots that facilitate the visualization of clustering quality. Reducing the dimensionality of data often enhances cluster interpretability, making it easier to identify key patterns or relationships that may be obscured in higher dimensions. Clustering techniques can be applied to data observations and features. By clustering similar or correlated features, you can identify sets that provide redundant information. This enables feature selection by choosing a representative feature from each cluster, reducing the total number of features while preserving valuable information. Clustering can help with feature engineering decisions. For instance, if clusters indicate distinct subgroups in data, specific interactions between features or certain transformations could benefit predictive modeling. Here's a simple simulation using a clustering method like k-means to cluster features. Each of the 5 features plotted here was generated with a random normal distribution with 3 different mean values, 1, 5, and 10, and variances of 1, except for feature number 4, which has a variance of 2. As you can see visually, features 1 through 3 are statistically very similar, with the same mean and variance. Features 4 and 5 stand out. Indeed, running k-means on the features, not the data values, with k equals 3 correctly, clustering the features. Cluster 1 contains redundant features, so if you were to do any modeling with this dataset, you would want to select only one of them. This is an example of implementing feature selection, part of feature engineering. You can also view it as dimension reduction. In this video, you learned to explain clustering, dimension reduction, and feature engineering and how they work well together to improve model performance, quality, and interpretability. Explain dimension reduction and how it is used as a pre-processing step for clustering, simplifying data structure, and improving outcomes. Analyze how dimension reduction is used for face recognition with eigenfaces as input features. Analyze how clustering can be used for feature selection to identify sets that provide redundant information. And finally, analyze feature selection using k-means to cluster features. Welcome to Dimension Reduction Algorithms. After watching this video, you will be able to explain what dimension reduction algorithms are. You will also be able to describe the different types of dimension reduction algorithms, namely PCA, T-SNE, and UMAP. Dimensionality reduction algorithms reduce the number of dataset features without sacrificing critical dataset information. High-dimensional data is often very difficult to analyze and visualize. Dimensionality reduction algorithms simplify the data set for machine learning models. The principal component analysis, or PCA, T-distributed stochastic neighbor embedding, or T-SNE, and uniform manifold approximation and projection, or UMAP, algorithms transform original dimensions to create new features. Principal component analysis, or PCA, is a linear dimensionality reduction algorithm that assumes dataset features are linearly correlated. It simplifies data, reduces dimensionality, and reduces noise while minimizing information loss. PCA can transform features into a new set of uncorrelated variables called principal components while retaining as much variance as possible. These principal components are orthogonal to each other and define a new coordinate system for the feature space. The principal components are organized in decreasing order of importance, or how much of the feature space variance they explain. The first few components often contain most of the information, while the rest tend to represent noise. T-distributed stochastic neighbor embedding, or T-SNE, maps high-dimensional data points to a lower dimensional space. It is good at finding clusters in complex, high-dimensional data that can be visualized in 2 or 3 dimensions and works well with data like images and text. tsne focuses on preserving the similarity of points that are close together and less so on distant points. Similarity is measured as proximity, using the distance between pairs of points. Unfortunately, tsne doesn't scale well and can be difficult to tune as it is sensitive to its hyperparameters. Uniform Manifold Approximation and Projection, or UMAP, is also a nonlinear dimensionality reduction algorithm, often used as an alternative to tsne. It constructs a high-dimensional graph representation of the data based on manifold theory, which assumes that the data lies on a lower-dimensional manifold embedded in higher-dimensional space. UMAP then optimizes a low-dimensional graph structure that best preserves the relationships between points in the original data. UMAP scales better than tsne, and, in addition to the lower structure of the data, preserves the global structure, often providing higher clustering performance than tsne. Consider the 3D plots showing simulated data using the makeBlobs function in Scikit-learn. The plots show the same 3D data from 2 different perspectives. There's a little bit of overlap between the yellow and purple clusters, while the other 2 blobs are distinctly separated from all blobs. Let's apply the PCA, tsne, and UMAP dimension reduction algorithms to project this data set onto 2 dimensions and compare the results. PCA has separated the blobs effectively. The blobs are all normally distributed, and the only differences between them are in their means and variances. This means the blobs are linearly correlated, so it is expected that PCA will perform well on the simulated data. tsne has clustered the data into 4 clusters and mostly separated the blobs well. The algorithm identified 4 very distinct clusters, with several mislabeled points within the purple cluster from the green and yellow clusters. This mixing is expected, as 2 of the clusters had a slight overlap. Although UMAP didn't perfectly identify some of the blob points in the blobs, you can see that 3 of the clusters did not fully separate. In particular, the yellow and green clusters have a slight overlap with the purple cluster. This should be the case for the yellow and purple clusters because these 2 clusters were not fully separated to begin with in the 3D input data. UMAP performs slightly better than tsne in this regard, since tsne identified 4 very distinct clusters. In this video, you learned that dimensionality reduction algorithms reduce the number of dataset features without sacrificing critical dataset information. There are different types of dimensionality reduction algorithms, namely PCA, tsne, and UMAP. PCA is a linear dimensionality reduction algorithm that simplifies data, reduces dimensionality, and reduces noise while minimizing information loss. tsne maps high-dimensional data points to a lower dimensional space. UMAP creates a low-dimensional representation of data by approximating the manifold on which the data lies. Welcome to Classification Metrics and Evaluation Techniques. After watching this video, you will be able to define the train test split technique, describe confusion matrix, accuracy, precision, recall, and F1 score metrics, and illustrate examples of each. Let's begin by understanding what supervised learning evaluation is. Supervised learning evaluation establishes how well a machine learning model can predict the outcome for unseen data. It is essential for understanding model effectiveness and involves comparing model predictions to ground truth labels. During training, the model tries to optimize predictions based on 1 or more evaluation metrics. After training, the model is again evaluated to estimate how well it can generalize to unseen data. Supervised learning evaluation is essential in both the training and testing phases. When you're training a machine learning model to predict an outcome, you don't want to feed all the data from the dataset to the model. The train test split technique is used to estimate the performance of machine learning algorithms when they're used to make predictions. In the train test split technique, the dataset is split into 2 parts, the training set and the test set. The training subset comprises around 70 to 80% of the data and is used to train the model. The test subset is used to evaluate how well the model generalizes to new unseen data. In classification tasks, the model predicts categorical labels to assess how well these predictions align with the actual labels. We'll explore some common metrics for evaluating classification models. Accuracy is the ratio of correctly predicted instances to the total number of instances in the dataset. A confusion matrix is a table that breaks down the number of ground truth instances of a specific class against the number of predicted class instances. Precision measures how many of the predicted positive instances are actually positive. Recall measures how many of the actual positive instances are correctly predicted. F1 score combines precision and recall to represent a model's accuracy. To calculate accuracy, consider a will I pass or fail my biology test example. Assume your model has been trained and has some predictions on the test set. You represent pass with green squares and fail with red. You can calculate accuracy by taking the number of correctly classified observations and dividing it by the number of observations. The misclassified points are highlighted in gray. That'll give you 70%. Displayed here is a confusion matrix commonly used for evaluating classification performance. On the y-axis, you have the true labels, and on the x-axis, you have the predicted labels. The numbers in the boxes are the counts of true positives, true negatives, false positives, and false negatives. True positive means you predicted pass, and it was pass. True negative means you predicted fail, and it was fail. False positives mean you predicted pass, but it is actually fail. False negative means you predicted fail, and it is actually pass. Shown here is the decision boundary for a KNN classifier trained to predict iris types based on the iris flower dataset in Scikit-learn. Accuracy is high at 93%. As you can see from the background colors, which distinguish the three prediction types, as compared with the dots colored by their actual types, there are very few misclassified flowers. Here, you see a heat map displaying the confusion matrix for the KNN classifier, colored on a scale ranging from purple at the lowest and yellow at the highest values. The colors represent the number of predictions made for each class that fall within each actual class. For example, for predictions classified as Setosa, the entries show the counts of how many of those predictions should have been Setosa, Versicolor, or Virginica. The diagonal entries are the predictions the classifier got right. The diagonal is hot in this case, which is good. When evaluating a classification model, a data scientist also considers other metrics. Let's look at the pass or fail example. In the pass class, precision is the fraction of true positives among all the examples that were predicted to be positives. Precision is the number of true positives divided by the number of positive predictions. An example where precision may be more important than accuracy is a movie recommendation engine where it may cost more to promote a certain movie to a user. If the movie was a false positive, meaning that the user isn't interested in the movie that was recommended, then that would be an additional cost with no benefit. Now let's take a look at recall. Recall is the fraction of true positives among all the examples that were actually positive. Consider the number of pass observations the model got right out of the total true pass observations. That is 4 out of 7, or 57.1%. It is the number of true positives divided by the sum of true positives and false negatives. When opportunity cost is more important, recall may be a more important metric. An example of this is in the medical field. It's important to account for false negatives, especially regarding patient health. Finally, let's look at the F1 score. Imagine that you were in the medical field and have incorrectly classified patients as having an illness. You could be treating the wrong diagnosis. In cases such as this, where precision and recall are equally important, you can't try to optimize one or the other. The F1 score, which is defined as the harmonic or balanced mean of precision and recall, is useful. It is calculated as 2 multiplied by precision and recall divided by precision plus recall. Here is a table summarizing the precision, recall, and F1 scores for each of the actual classes: Setosa, Versicolor, and Virginica. Setosa predictions scored perfectly at 1 for each metric. The weighted average of the metrics is weighted by the support of each class, or number of flowers in each class. In this video, you learn that supervised learning evaluation establishes how well a machine learning model can predict the outcome for unseen data. The train test split technique is used to estimate the prediction performance of machine learning algorithms for unseen data. Common metrics for evaluating classification models include accuracy, confusion matrix, precision, and recall. The F1 score is the harmonic or balanced mean of precision and recall. Welcome to Regression Metrics and Evaluation Techniques. After watching this video, you will be able to explain the need to evaluate regression models, define the error of a model, and describe certain regression metrics and evaluation techniques. You will also be able to compare different regression metrics. Did you know that regression models are not foolproof? They often make prediction errors. Evaluating a regression model involves determining how accurately the model can predict continuous numerical values, such as exam grades. Consider a scenario where you want to predict your grades for your final exam after receiving your midterm scores. You have fit your regression line. The blue dots are the grades you've received. The differences between the line and the blue dots are called errors, the predicted values minus the actual values. In the context of linear regression, the error of the model is a measure of the difference between the data points and the trend line generated by the algorithm. Since there are multiple data points, an error can be determined in various ways. Regression metrics provide insight into a model's performance, such as its accuracy, error distribution, and error magnitude. There are 4 metrics that are the most important in regression. MAE, or mean absolute error, is the average absolute difference between the values fitted by the model and the observed historical data. MSE, or mean squared error, is the sum of the squared difference between the values fitted by the model and observed values divided by the number of historical points minus the number of parameters in the model. RMSE, or root mean squared error, is the square root of the MSE. This is a popular evaluation metric because it has the same units as the target variable, making it easier to interpret than MSE. R squared is the amount of variance in the dependent variable that the independent variable can explain. It is also called the coefficient of determination and measures the model's goodness of fit. The values range from 0 to 1, with 0 being a badly fit model and 1 being a perfect model. Values between 0 and 1 are what you can expect from real-world scenarios, as there is no perfect model in real life. Consider these evaluation metrics, which compare a model's predicted values, yi hat, with the actual values, yl. No single evaluation metrics can give you a universally good measure of goodness of fit. You need to visualize your results. Plot the actual and predicted values for your model to see how well your regression model fits the labels. Explained variance is the sum of squared differences between the predictions and the average value of the actual target data. For a perfect predictor, explained variance is the same as the total variance of the target, where total variance, usually denoted as sigma squared, measures the total variable of the target values from their mean value. R squared is a popular evaluation metric that measures the proportion of variance in the target variable that is predictable from the input variables. R squared is a simple measure for describing model performance, claiming that the model explains 85% of the variation in the outcome is readily understood by non-technical people. It is important to remember that R squared assumes the target is linearly related to the input features. It can be misleading for nonlinear models. If the model perfectly predicts all data points, in that case, yi hat equals yi for all I, the explained variance is identical to the total variance, and the unexplained variance is 0. Thus, R squared is 1 for a perfect model. Suppose the model's predictions are extremely simplistic, constantly predicting the mean of the data for every data point. In that case, it doesn't explain any variance because the explained variance is 0, and the total variance is then precisely the unexplained variance. Thus, the R squared is 0 for the simplistic mean value model. Negative R squared values mean the model performs so poorly that unexplained variance exceeds total variance. 3 linear regression results are shown here based on a simulated target variable with an exponential distribution, commonly known as log normal distribution. The linear model fits 3 versions of the target variable: the original target, a Box-Cox transformed version of the target, and a logarithmically transformed version. Visually, you can see that the models progressively fit the target data better and better because the data becomes more concentrated around the best fit line with each transformation. The various evaluation metrics displayed for each of the 3 models fit to the transformed targets are all consistent with our visual intuition of the result. R squared increased significantly for Box-Cox and log transformations, and the error metrics, MAE, MSE, and RMSE, all improved substantially. In this video, you learned that evaluating a regression model involves determining how accurately the model can predict continuous numerical values. The error of the model is a measure of the difference between the data points and the trend line generated by the algorithm. The essential regression metrics are AME, MSE, RMSE, and R squared. Explained variance is the sum of squared differences between the predictions and the average value of the actual target data. R squared measures the proportion of variance in the target variable that is predictable from the input variables. Welcome to this video on evaluating unsupervised learning models, heuristics, and techniques. After watching this video, you will be able to explain the evaluation of unsupervised learning models and their role in assessing the quality of patterns and models. You will also be able to differentiate between the different types of heuristics and how they evaluate cluster quality. You will then analyze different internal and external clustering evaluation metrics to assess clustering results. Finally, you'll evaluate dimensionality reduction to measure how well-reduced data retains important information. Evaluating unsupervised learning models poses unique challenges compared to supervised models, as there are no predefined labels or ground truths for training. Unsupervised techniques, like clustering and dimensionality reduction, aim to discover hidden patterns and structures in data. Therefore, evaluation methods assess the quality of these patterns and how effectively the model groups similar data points. Unsupervised learning results are often subjective, requiring careful evaluation for consistency. Stability is crucial in assessing model reliability, ensuring the model performs similarly across varied data subsets or perturbations. For example, a stable clustering model produces similar clusters despite changes in the dataset. There's no one-size-fits-all approach to evaluating unsupervised learning models. A combination of methods is essential. Effective evaluation often combines heuristics, domain expertise, metrics, ground truth comparisons, and visualization tools to assess the quality of learned patterns. In clustering, the goal is to group similar data points into clusters. Unsupervised learning lacks predefined labels, so various heuristics are used to evaluate cluster quality, including internal evaluation metrics, which rely on input data, external evaluation metrics, which use ground truth labels when available, generalizability or stability evaluation, assessing cluster consistency across data variations, dimensionality reduction techniques for visualizing clustering outcomes, such as scatter plots. Cluster-assisted learning, refining clusters through supervised learning evaluations. Domain expertise is also invaluable for providing feedback and interpreting clustering results. Internal clustering evaluation metrics assess clustering quality based on the input data. Here are some commonly used metrics. Silhouette score compares cohesion within each cluster to separation from others, ranging from -1 to 1, with higher values indicating better defined clusters. The Davies-Bouldin index measures the average ratio of a cluster's compactness to its separation from the nearest cluster, with lower values indicating more distinct and compact clusters. Inertia in k-means clustering calculates the sum of variances within each cluster. Lower values suggest more compact clusters, but increasing the number of clusters reduces variance, creating a trade-off. These are clustering results from applying k-means to simulated blobs, where the clusters are distinctly separated and dense. The silhouette plot on the right shows the identified clusters in different colors. Each bar represents the silhouette coefficients for points within each cluster, combining the distance to the nearest neighboring cluster and the average distance to other points in the same cluster. The vertical red dashed line indicates a high average silhouette score of 0.84. The Davies-Bouldin index is low at 0.22. Both metrics suggest excellent clustering quality. These are clustering results from k-means on simulated blobs, where the clusters are distinct but somewhat dispersed. The silhouette plot shows coefficients decreasing rapidly as clusters spread out, with a few negative values indicating potential misassignments to clusters. The silhouette score is moderately high at 0.58, and the Davies-Bouldin index is 0.6, both suggesting reasonable clustering results. External clustering metrics used labeled or ground truth data to evaluate clustering quality by comparing cluster labels with known classes. Adjusted Rand index measures the similarity between true labels and clustering outcomes, ranging from -1 to 1. A score of 1 indicates perfect alignment, 0 indicates random clustering, and negative values suggest worse than random performance. Normalized mutual information quantifies shared information and between predicted cluster assignments and true labels on a scale from 0 to 1, where 1 indicates perfect agreement and 0 indicates no shared information. Folks-Mallow's index is the geometric mean of precision and recall based on clustering and label assignments, with a higher score indicating better clustering performance. When using dimensionality reduction techniques like PCA, TSNE, or UMAP, it's crucial to evaluate how well the reduced data retains important information. Explained variance ratio in PCA measures the variance captured by principal components, helping determine how many are needed for acceptable cumulative explained variance. Reconstruction error assesses how accurately the original data can be reconstructed from the reduced representation. Lower values indicate better information preservation. Neighborhood preservation evaluates how well relationships between data points in high-dimensional space are maintained in lower dimensions, especially for manifold learning algorithms like t-SNE and UMAP. This scatter plot shows the first two principal components, PC1 and PC2, from the PCA analysis of the iris flower datasets, with points color-coded by species, setosa, versicolor, or virginica. PC1 is dominant, nearly separating the clusters as indicated by vertical lines. With 4 features in the iris dataset, direct visualization of classes is challenging. PCA allows for indirect visualization using just 2 dimensions. This bar plot shows the explained variance for each principal component in descending order. The red dashed line indicates the cumulative explained variance. The first 2 components account for most of the variance, while additional components don't add much. Effective model evaluation requires diverse metrics and domain expertise to assess patterns. Subjective analysis and visual tools, like scatter plots, dendrograms, and projection methods such as PCA, t-SNE, and UMAP, are essential for interpreting unsupervised learning results. In this video, you learned to explain the evaluation of unsupervised learning models and their role in assessing the quality of patterns and models. Explain unsupervised learning results and how stability ensures that models perform consistently. Differentiate between the different types of heuristics and how they evaluate cluster quality. Analyze different internal clustering evaluation metrics such as silhouette score, Davies-Bouldin index, and inertia. Evaluate internal clustering by applying k-means to simulated blobs. Analyze external clustering evaluation metrics with the adjusted RAND index, normalized mutual information, and Folks-Mallows index. Evaluate dimensionality reduction with explained variance ratio, reconstruction error, and neighborhood preservation. Welcome to cross-validation and advanced model validation techniques. After watching this video, you will be able to define model validation. You will also be able to explain what data snooping is and how to avoid it. Finally, you will be able to discuss key strategies for model validation. Model validation is all about doing your best to optimize your model without jeopardizing its ability to predict well on unseen data. It helps you prevent overfitting when selecting the best model configuration by tuning hyperparameters. Consider the basic train or test split evaluation method, where the dataset is split into 2 parts. A training set is used to train the model, and a test set is used to evaluate or estimate the model's ability to predict outcomes from unseen data. Most machine learning models have optional parameter settings, called model hyperparameters, that affect how well the model fits the data used to train it. What if you tried different hyperparameters for your model and then chose the one that performed best on the testing data? Wouldn't you effectively fit the model to the testing data, not the training data? This would result in overfitting. Your model likely wouldn't generalize well to unseen data, invalidating it. Checking performance on the test data before you are done optimizing your model is called data snooping, a form of what's known as data leakage. What can you do to validate your model to ensure it doesn't overfit itself to your test data? You need to decouple model tuning from the final evaluation. Validation means tuning your model on the training data, but only testing it on unseen test data once you are satisfied that it is well trained. There is no snooping involved. Here is a model validation strategy that involves segmenting your data into at least 3 parts. A training set, which is used to train the model, including optimizing its hyperparameters. 1 or more validation sets or subsets of the training data used during the model optimization process to evaluate a machine learning model's performance. A test set that is held back, unseen data used for final evaluation after model training and validation. Cross-validation enables hyperparameter tuning. Here's the cross-validation algorithm for model tuning and validation. Split your data into training data and testing data. Further split your training data into a training set and a validation set. Optimize your model's hyperparameters by repeatedly training it on the training set and measuring its performance on the validation set. Choose your best set of hyperparameters and evaluate your resulting best model on your completely unseen testing data. You now have a validated model and an estimate of how well it will generalize on new unseen data. Some potential validation problems reside in selecting a single, specific validation set. Your model could be overfitting to this specific data set. If your model needs a lot of data to train on, you may not have enough data left over for validation and testing purposes. This means your training and validation data might not be representative of the sample population. Your model may not be learning details, like noise on this particular set. Your model's performance may not be stable across different validation sets. A solution to avoid overfitting your test data while trying to optimize the model's hyperparameters consists of a few key steps. Divide your data into k equal sized folds to be used as validation subsets. For each trial model or set of hyperparameters, and for each fold, train a model on the remaining k-1 folds. Test the model on the selected fold and store this model's score. Compute an aggregated score of overall folds. Select the set of hyperparameters that led to the best model. Notice that every data point is used both for training and validation, greatly increasing the utilization of the data you have on hand. K-fold cross-validation, typically 5 to 10-fold, provides a more robust technique for estimating your model's generalizability to unseen real-world data. Varying the validation set has several benefits. It greatly increases the data on which the model trains and tests. It reduces overfitting because it smooths out unwanted details that are particular to a chosen training subset. Consequently, it improves your ability to evaluate how well your model will generalize to unseen data. In classification problems, you might have many observations in one class and very few in another. It means you are dealing with an imbalanced classification problem. Stratified cross-validation ensures that the class distribution is preserved in each validation fold, preventing bias in the evaluation process. The analog to imbalanced data in regression problems is when your target is highly skewed. Many models assume your target is normally distributed. Fortunately, you can transform your target variable using methods like log or box-cox transforms to reduce the skewness and fit your model to the transformed target. Consider an example of a skewed target variable as depicted by the histogram on the left. Lower target values have a much higher frequency than higher values. The other two histograms illustrate the distributions of box-cox and logarithmic transforms of the target data. Both transforms significantly reduce the skewness. Observe how well linear regression can fit each of these representations of the target variable. In this video, you learned that model validation helps you prevent overfitting when selecting the best model configuration by tuning hyperparameters. Checking performance on the test data before you are done optimizing your model is called data snooping. Model validation involves dividing data into training set, validation set, and test set. Cross-validation enables hyperparameter tuning. A solution to avoid overfitting your test data while trying to optimize the model's hyperparameters is k-fold cross-validation. Stratified cross-validation ensures that the class distribution is preserved in each validation fold, preventing bias. Welcome to regularization in linear regression. After watching this video, you will be able to define regularization for linear regression and compare linear, ridge, and lasso regression methods. Regularization is a regression technique to prevent overfitting. It constrains the model during training, discouraging it from overfitting to the training data. Regularization achieves this goal by suppressing the size of its coefficients. With regularization, a modified cost function is used to optimize the linear regression model, which has the general form regularized cost function equals mean squared error plus lambda times penalty term. Here, lambda is a parameter that controls the influence of the penalty term, and the penalty measures the size of the coefficients. Common regularized regression methods like ridge and lasso regularization use specific penalty terms. Linear regression models the relationship between two or more variables by fitting a straight line to the given dataset. In ordinary linear regression, predictions are a linear combination of features, and the goal is to minimize the loss function, usually measured as the mean squared error, MSE, between the predicted and actual target values. Mathematically, the linear regression model is defined by a linear combination of the form y hat equals theta 0 plus theta 1 x1 plus theta 2 x2 plus theta n xn, where the xi are the feature vectors that can be represented as a matrix X that includes a constant value of 1 in the first entry to account for the bias, or intercept term theta 0, and the thetas are the unknown weights, which can be represented as a matrix theta. The weights are commonly referred to as the coefficients of the linear regression model. Ridge and lasso are regularized forms of linear regression that differ only in their cost functions. Regular linear regression has no penalty term, while ridge regression uses an L2 or sum of squares penalty on its coefficients, which helps to shrink them. Lasso regressions use an L1 or sum of absolute values penalty on its coefficients. This penalty can shrink some coefficients to exactly 0. Lasso regression responds well to feature sparsity, making it useful for feature selection and data compression tasks. In machine learning, sparse coefficients mean that only a small number of variables significantly contribute to a dataset, while the remaining have little or no impact. The plot here shows a simulated set of sparse coefficients labeled as black dots with a high signal-to-noise ratio, SNR. The simulation displays coefficient values for each of the 100 features. It has 5 non-sparse coefficients with a high SNR, meaning they stand out strongly. As you can see, all 3 regression methods predict the non-zero coefficients very well. Lasso finds the 0 coefficients exactly, while linear and ridge have some difficulty predicting the 0 coefficients, with linear regression doing slightly better than ridge regression. In this plot, we have a simulated set of sparse coefficients labeled as black dots, with a low SNR. Evidently, linear regression performs very poorly in this case, as it tends to greatly overestimate the ideal coefficients, overshoot most of the 0 coefficients, and assign large negative coefficients when they should be 0. This illustrates the fact that ordinary linear regression is sensitive to noisy data. As you can also see, ridge and lasso have similar abilities in predicting the non-zero coefficients, but lasso is much better than ridge at finding the 0 coefficients. Even in this low SNR environment, lasso is a great feature selector. This plot shows non-sparse coefficients with a high SNR. As you can see, all 3 regression methods predict the non-zero coefficients very well, with the ridge erring slightly more than the others. Lasso finds all of the 0 coefficients, while linear and ridge have some difficulty predicting the 0 coefficients, with linear regression doing slightly better than ridge regression. In this plot, we have non-sparse coefficients with a low SNR. Evidently, linear regression performs very poorly in this case. It tends to overestimate the ideal coefficients, overshoot most of the 0 coefficients, and assign large negative coefficients even though all coefficients here are positive. This illustrates that ordinary linear regression is sensitive to noisy data. As you can also see, ridge regression slightly outperforms lasso when it comes to predicting the non-zero coefficients, but lasso is better at finding the 0 coefficients. Even in this low SNR environment, lasso is a great feature selector. This chart displays the results of training lasso, ridge, and regular linear regression for a moderately noisy target variable. The results show the predictions made on the test data after each model was trained on 70% of the dataset. The top row shows 3 scatter plots, comparing test predictions against the actual lasso, ridge, and regular regression test values. The result for lasso is much more concentrated around the ideal 45-degree line than the other 2 results. The bottom row of plots illustrates the exact comparisons instead of 2 superimposed plots of the regression predictions and actual values. Again, you can see that lasso outperformed both ridge and regular regression because its predictions track well with the actual values. In addition, the MSEs are displayed for all 3 models. The MSEs for lasso is about 30 times less than the MSEs for ridge and regular linear regression. This table summarizes the relative performances of linear, ridge, and lasso regression methods in high and low SNR environments for sparse and non-sparse coefficients. In all scenarios, lasso performs the best out of the 3 methods. Regular linear regression performs well in high SNR environments and poorly in low SNR environments. The methods rank similarly whether the SNR is high or low, with the ridge holding its rating in all cases. For low SNR, lasso and ridge are clear winners. In this video, you learned regularization is a regression technique to prevent overfitting. It constrains the model during training, discouraging it from overfitting to the training data. In ordinary linear regression, predictions are a linear combination of features, and the goal is to minimize the loss function. Ridge and lasso are regularized forms of linear regression that differ only in their cost functions. Regular linear regression has no penalty term, while ridge regression uses an L2, or sum of squares penalty, on its coefficients, which helps to shrink them. Lasso regressions use an L1, or sum of absolute values penalty, on its coefficients. Linear regression suffers from overfitting in the presence of noise because it is highly sensitive to outliers. You can use regularization techniques in conjunction with linear regression to mitigate such errors. Welcome to data leakage and other pitfalls. After watching this video, you will be able to define data leakage and explain how to mitigate it. You will also be able to describe feature importance interpretation and other modeling pitfalls. Imagine you want to train a model to predict house prices. Along with historical data like square footage, you engineer a feature using the average of the actual home prices over the entire data set. You are pleased to see how well your model performs on the test data. However, your model was taught using data that was leaked from the future and that it can't access in production. Without this access, deploying your model won't perform as well as you thought it would, given the test results. Data leakage occurs when your model's training data includes information that would not be available in the real world, such as unseen data after deployment. Data leakage deceives your model, leading it to perform misleadingly well during training and validation. Since your test dataset will also contain this leaked data, evaluation won't detect the poor generalizability until you implement your model into production. Data snooping happens when the training set contains information about the testing set or the model sees data it shouldn't have access to. This can occur when you include future information when predicting outcomes, such as tomorrow's stock price, to predict today's. It can also take place while engineering new features using the entire dataset. Data processing pipelines should be run independently on the training and testing data. To mitigate the data leakage risk, you must carefully select training and testing data. If any future data leaks into the training data, you have a problem. Let's look at what mitigation measures you can take. Avoid features like global averages or other statistics derived from the entire dataset. Ensure proper separation between your training, validation, and test sets, avoiding overlap or contamination. Ensure that none of your features contain unavailable information when making real-world predictions with your deployed model. Pay attention to how you implement cross-validation to ensure you aren't leaking data across different validation folds. This is particularly important when using time-dependent data. In this case, you should use a time series split rather than the usual train test split. To avoid leakage when using cross-validation to tune your model's hyperparameters, fit your pipeline separately to each training fold and apply the resultant fitted pipeline to its corresponding validation fold. Assuming you have imported the required libraries, loaded your data, and taken precautions to ensure you don't already have any data leakage, consider this Python code for training a classifier. First, you split your data into training and test data sets. For this example, assume this is a valid method for your dataset and no temporal or other leakage contamination will occur. Then, define a pipeline of 3 models, a scalar, PCA, and a KNN classifier. Next, a parameter grid consisting of a set of values is set up to try for a number of PCA components and the number of neighbors in KNN. Now, optimize your model by performing a grid search using cross-validation. It is important to notice here that the pipeline is input to the grid search. This ensures that the pipeline is applied separately to each training fold and its corresponding validation set. After finding the best parameters, you evaluate your final model on the first set you held back to get an unbiased estimate of your model's performance in the wild. If your data is temporal, where the order of your data points in time is crucial, you want to avoid randomly splitting it into training and test sets. Instead, you need to split your data into sequential training and testing sets, ensuring that the training set always precedes the test set. Modifying your code to implement time series cross-validation is easy. Instead of using train test split, you would use time series split and specify that you want to use this cross-validation method during hyperparameter tuning by setting CV equals TSCV in grid search CV. In this example, Scikit-learn's time series split splits your data into 4 equal-sized folds, retaining their temporal order. Each split uses a portion of the data from the past for training and the remaining future data for validation. The training set expands to include more data with each split while the test set shrinks. Understanding some common pitfalls and assessing feature importances provided by a trained machine learning model is essential. Highly correlated or redundant features used in modeling result in shared importances, which lowers their apparent influence. Further, blindly selecting what seems to be the most important features to use in subsequent modeling can cause a significant feature to be selected to degrade your results. Some algorithms, like linear regression, don't naturally account for the scale of features so that unskilled data can distort importance rankings. Feature importance indicates correlation, not causation. Important features don't necessarily drive outcomes. Some models rank individual feature importance without accounting for interactions, potentially underestimating or overestimating their combined impact. For example, suppose you have two features that don't provide enough information for linear regression to perform well. Still, their interaction or product boosts the linear regression performance. Then, a nonlinear algorithm like random forest regression could implicitly detect this interaction, leading to good performance. For linear regression, the separate features would erroneously seem unimportant. At the same time, their importance would be shared for random forest, and you would have no idea that their product is the crucial explanatory variable. Here are some common modeling pitfalls to consider. Using raw data without appropriate feature selection or transformation prevents you from discovering your optimal model. Choosing the wrong evaluation metric or misinterpreting metrics can mislead your evaluation. Failing to address class imbalances and classification problems biases your predictions towards the majority classes. Automated machine learning tools can be powerful, but you still need to understand your data and the model the system creates for you. It is crucial to understand that if your model lacks features that have a causal impact on the target variable, then the what-if scenarios generated by the model may be invalid. Without causal relationships, your model's predictions based on hypothetical changes can be highly misleading or inaccurate. In this video, you learned that data leakage occurs when your model's training data includes information that would not be available in the real world or unseen data after deployment. You can mitigate data leakage by avoiding overlap or contamination between training, validation, and test sets, ensuring training features are available for real-world deployment, using cross-validation carefully, and hyperparameter tuning. Some common pitfalls in assessing feature importances provided by a trained machine learning model are feature redundance, scale sensitivity, assuming causation, and overlooking feature interactions. Other modeling pitfalls include selecting inappropriate features, misinterpreting evaluation metrics, ignoring class imbalance, blind reliance on automation, and performing what-if scenarios based on non-causal data.